Hello, everyone. Welcome to the May 2024 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. One of the downsides of doing a podcast for any number of years is that some of your former guests will pass away, and that is always a sad event. Last year, of course, we had a couple of instances. Herb Gintis and Mari Rudy both died. And already this year, two people who were former guests have passed away, Frans de Waal and Daniel Dennett. Frans de Waal was an amazingly successful and influential primatologist and anthropologist. He studied primates and compared them to young humans and found fascinating commonalities as well as differences. And we did a great podcast with him that I had no idea that he was sick. I don't even know a lot of the details of his passing away, but that was very sad. Whereas Dan Dennett, is not only a hugely important philosopher for the 20th and 21st century, and a Mindscape guest, but also a personal friend. So that hit very hard. I was sitting at a table with Dan and a bunch of other philosophers just a few weeks ago at Santa Fe, and he was fine, right? But, you reach a certain age, he'd already had a couple of heart issues that were very, very serious, and so this can happen. I'm sure Dan would be the first one to say that we should, appreciate what he did while he was here, but the idea of dying is inevitable, and we should move on and think about it. But many people for this month's AMA asked me to say something about Dan and his influence and his contributions and what he meant to me. And so I'm going to do that right here in the intro before we get to the AMA itself. I will mention that there was an article in Ars Technica that Jennifer Willett, my wife and also science writer, contributed, sort of a memorial to Dan. It wasn't like strictly an intellectual obituary or anything like that, but it was more personal, more reflective, both on his work and on who he was as a person. And, by the way, there was a New York Times article, obituary after Dennett died that was just terrible. I mean, it got all the philosophy wrong. It said he was a staunch opponent of free will, even though he was actually the leading compatibilist about free will in the world. And mostly it quoted his enemies, people who had said terrible things about him in print. I don't know what was going on with the New York Times obituary. But Jennifer's article, which I will link to on the website, preposterousuniverse.com/podcast, she talked to a bunch of people and got some great quotes. I just want to read you two quotes about Dan Dennett. One was from David Wallace, who was another Mindscape guest. And in fact, at this Santa Fe conference a few weeks ago, David was also there, and I had the extreme privilege of introducing Dan to David Wallace. They'd never met each other before, even though David was the first to say that Dan's philosophy was enormously influential on him. David's famous book on the many worlds interpretation of quantum mechanics is titled The Emergent Multiverse, and his notion of emergence leans very, very heavily on Dan's idea of real patterns that he talks about. So, David, was very happy to meet him, and said that his philosophical ideas absolutely permeated a lot of David's work. And in fact, I think one of the regrets of Dan passing away is that he didn't really engage that much with physics over the course of his philosophical career. And I was very interested in getting him more into physics, and he was receptive to this. He was interested. He wanted to learn more about it. And, alas, that's not going to happen right now. In fact, it just really hurts me because I am finishing a paper with a student at Truth Parola that is going to appear in a volume of essays dedicated to responding to Dan's idea of real patterns and what they say about emergence. And Dan was going to read all the papers that were contributed and then respond to them. And I really wanted to hear what he had to say about what we were going to say. And now we're not going to have that happen. So it's very, very sad for all sorts of reasons. And that's okay to be sad about it. You can know it, you can accept it, you can appreciate the inevitability of these things while still being sad about it. Anyway, here is the quote from David Wallace that was in Jennifer's article. To me, Dan Dennett exemplified what it means to do philosophy in an age of science. He once said there was no such thing as philosophy-free science, only science that didn't interrogate its philosophical assumptions. Equally, he saw more deeply than almost anyone that the deepest traditional questions of philosophy, from free will to consciousness to metaphysics, were irreversibly transformed by modern science, most especially by natural selection. His approach, as much as his own towering contributions, has inspired generations of philosophers, far beyond cognitive science and the philosophy of mind. His ideas have been influential in the interpretation of quantum theory, for instance. He was one of the great philosophers of the last century and one of the very few whose work has been transformative outside academic philosophy. I think that last point is crucially important. One of the things about Dan is that he was, you could make a short list, but he was certainly one of the most publicly influential philosophers that we had. We don't have a lot. We have far fewer publicly recognizable philosophers than scientists. And I don't know whether that's good or bad or whatever, but Dan did his job in getting philosophical ideas a lot of public engagement, which I obviously think is super duper important. In fact, most of his books were very intentionally written in a way that they were intellectual contributions and also readable by the general public. And that's one of the many ways in which he influenced me. I really aspire to live up to that. Sometimes I write books like the recent books, The Biggest Ideas in the Universe, are purely pedagogical. But books like From Eternity to Here or The Big Picture or Something Deeply Hidden, I'm very, very explicitly trying to make an academic level argument in a way that can be appreciated and read by people without academic backgrounds. And the guy who has done that the best was Dan Dennett. And I know that, and he's the role model for doing that. The other thing that David mentions in that little quote is that Dan, was, he was naturalism was his guiding star, right? Like he was interested in connecting the scientific image to the manifest image of the world. These are phrases from Wilfrid Sellars, but if you've ever heard me say those phrases, the scientific image and the manifest image, I got them from Dan Dennett. He's the one who talked that way, and like many, many things that he would say, this is what makes a good thinker. Like they'll say something, you'll go, oh, yeah, that's the right way to think about it, right? Sometimes the mark of a great academic thinker is that you work very carefully through a long, involved argument and you come out the other side being impressed with the edifice that has been built. Other times, like you're circling around a kind of idea and someone can just pinpoint it, put their fingers on it and go, yes, that's what I'm trying to get at. And that was one of his geniuses. He was always very good at that. The other quote I wanted to read was from Douglas Hofstadter. Doug Hofstadter, obviously super famous guy, author of Gödel, Escher, Bach. And after Dan passed away, they were very close collaborators. And Hofstadter sent around an email to a bunch of people who he knew were friends of Dan, the little reflections email. And I asked permission of Doug to let Jennifer quote it, and he kindly gave permission. So here is Douglas Hofstadter. Dan was a deep thinker about what it is to be human. Quite early on, he arrived at what many would see as shocking conclusions about consciousness, essentially that it is just an emergent effect of physical interactions of tiny inanimate components. And from then on, he was a dead-set opponent of dualism, the idea that there is an ethereal, non-physical elixir called consciousness over and above the physical events taking place in the enormously complex substrate of a human or animal brain, and perhaps that of a silicon network as well. Dan thus totally rejected the notion of qualia, pure sensations of such things as colors, tastes, and so forth, and his arguments against the mystique of qualia were subtle but very cogent. And I wanted to say that because I think that Doug Hofstadter puts into words better than I could what Dan's primary preoccupation as a philosopher was, which was understanding the mind and consciousness from a naturalist, physicalist point of view. But, he was the leading guy in trying to make the world think that we didn't need anything spooky to understand consciousness, that we didn't need to change or violate the laws of physics. And so that, that's not something that I personally have thought about that much. I completely agree that you don't need to change the laws of physics, but Dan was much more at the detailed level, talking to neuroscientists, et cetera, to see how it actually works in the brain. And he had his ideas, and other people had different ideas, and who knows? I don't know whether we've really settled on the right idea yet or come up with it, but that was what he cared about the most. One question I've gotten is, what should I read by Dan Dennett? What were his most important books? I think that the two bangers in terms of popular level books or popularly accessible books are Consciousness Explained. That was his sort of magnum opus, trying to understand consciousness, and Darwin's Dangerous Idea, where he thinks a lot about evolution and its role. Dan was famous, probably became most famous in the public eye for being one of the four horsemen of new atheism, along with Richard Dawkins, Sam Harris, and Christopher Hitchens. But, those four people are not created equal in terms of what they did for the idea of atheism, etc. Dan was the careful thinker among those four people. They're all four smart people, but, there's some efficaciousness in terms of rhetoric and, rabble raising, if you want to call it that the four of them shared. But Dan was the professional philosopher among that group. And, he really thought through, okay, if you don't believe in God, then how did all this wonderful complexity, in particular conscious awareness, et cetera, come into existence? There's a slightly more technical book that he's written called The Intentional Stance, which I think is super important for thinking not only about consciousness, but also about artificial intelligence and things like that. He was actually, in the last year or two, super interested in AI and what it was doing. And the idea of the intentional stance, I'm probably going to bungle it here because I'm not an expert, but the basic idea is, at what point do you take a system that is just a bunch of inanimate atoms collecting together, and at what point do you attribute to it intentionality or agency, right? Like, at what point do we say, okay, I'm going to treat this thing as something that is thinking and planning for the future, something that we might call conscious or an agent or having free will and things like that. So he thinks through those questions very, very carefully. Anyway, it's a great loss to not have Dan around anymore. He was a wonderful person as well as a wonderful philosopher, mischievous, and he had a spark in his eye, twinkle in his eye at all times, and that's why he's such a great role model for so many, many other reasons. I'm very glad that at least we have a lot of record of his writings, having him on videos and things like that. He was one of the participants in the Moving Naturalism Forward workshop that I organized a while back. We didn't agree about everything. Like, you don't agree about everything. I don't agree about anything with anyone, really. So it's not a surprise that I didn't agree with Dan about everything. But honestly, I agreed with him about most things. It was very, very easy to talk to him about a whole bunch of things. And not going to be able to do that anymore, which is terrible. But he would... There's a siren outside my window. Sorry about that. People sometimes ask, why are there so many sirens outside your window? It's not because we live in a war zone. It's because we live very close to a hospital. Those are ambulance sirens that you're hearing. But anyway, yeah, so we're going to regret not having Dan around anymore. And life goes on, and more people will come up and do great things. And that's how things should be. So with that, let's go. Alex Thu says, can you comment on the college campus protests currently ongoing? Where do you draw the line between freedom of expression and illegal activity? If you were a university leader or administrator, how would you handle the situation differently, if at all? This is obviously a complicated situation. People don't like complicated situations. They want to put situations into boxes that are relatively black or white. I'm all in favor of campus protests. I think this is one of the things that college students are good at doing, not putting up with some established way of being and trying to make the world a better place and getting indignant about it. I mean, going to college, if you do it right, it can be quite an experience intellectually, emotionally, in terms of how you think about the world. For many people, when you go to college, you're living there. This is the first time in your life, or maybe one of the small numbers of times in your life, where you're in a completely different environment. completely different sets of people. You're not with the same people over and over again. You're maybe not living with your family. And you're exposed to all these new ideas from other students, from professors in classes, from books and things that you're reading and so forth. It is no surprise that college students, who are also at the same time still young and energetic, right? They're not settled into ruts, are going to be outraged by things happening in the world that they are catching on to and realizing are unjust, and they want to change. So in general, I think that the first response of college administrators to protesting students should be that that's good. That's part of what the college experience is all about. Of course, another feature of being a college student is that you're not that wise in the ways of the world as yet, right? You can get overly enthusiastic about things because you've recently discovered them and you're a new convert, and that happens. There was a thing going around on the internet which purported to be a list of demands from students at Cornell as part of the recent protests. I don't even know if it was legit or not, but it is emblematic of something that does happen, which is that despite the fact that the protests were nominally about the conflict between Israel and Palestine right now, there was a bunch of demands stuck in there about indigenous lands and having students have the right to help, choose faculty members, and a bunch of things that had nothing to do with what was going on in Gaza, which illustrates, I think, a broader problem, which is that these kinds of protests are often not very well targeted to actually make a difference, to actually get something done. It is often unclear what the goals are, what the realistic things that could happen would be, and often there's a spirit that compromise is bad, right? There's a weird tension. There are students protesting on the basis that they would like to see Israel and Palestine sit down and work out their differences and compromise. But they themselves are unwilling to compromise with Joe Biden, right? Because he's insufficiently radicalized about these particular ideas. I'm getting onto my own little hobby horses here. I think that in the modern world, we're not very good at compromising. We've given up or somewhat lost that ideal of democratic governance where we're supposed to talk to our enemies, right? You don't make peace with your friends, you make peace with your enemies. And that's something that student protesters are not especially good at. The strategic part of politics, who to compromise with, how to get your goals actually to come true in some way. So I think that, you have to understand that the protests are going to be kind of messy and chaotic and et cetera, and that's also okay. If the protests are just like sitting in the yard, singing some songs, giving some demands out there, then I think that the university administrators should bend over backwards to let them happen. One very obvious thing is that a lot of administrators just don't talk to the protesters. Their first instinct seems to be to call in the cops, which is not good for anybody. In Philadelphia, I know, when the University of Pennsylvania called in the cops on the protesters, the cops said no. They're like, we don't see any evidence that anything actually violent or dangerous is happening here. Just go and talk to them, right? And you know that when the cops are saying, like, you're being a little bit too violent in your reaction here, then maybe you should rethink your strategy a little bit. Of course, it is possible for protesters to go overboard. Of course, well, then there's many different ways of going overboard. One way of going overboard is just to say horrible things, right? There have been multiple examples of protesters saying things online or on videos that are terribly anti-Semitic or racist or whatever. Those people exist. Those people are real, right? And they're saying terrible things. And that doesn't necessarily undermine the legitimacy of the protest overall or of the cause. That all sides have bad people saying bad things about them. You should think about the best arguments for both sides, not the worst arguments. When it comes to the students like damaging property or stopping classes from going on, then it becomes a legitimately difficult case-by-case basis kind of call, I think. On the one hand, it is true that protests, in order to get their message out, will sometimes break the rules, right? That has been true forever. Certainly, the Boston Tea Party did not play by the rules that had been laid down. The various civil rights demonstrations did not always play by the rules that the local communities had put up. Sometimes to make progress, you have to break the rules, occupy a building, stay out even though you're told to go home, things like that. On the other hand, again, I would personally want the protesters to think strategically when they are getting in the way of people, when they are stopping people from having classes, for example, or whatever. Are the people who they're inconveniencing actually the ones who have a power to do something, right? If you're going on strike, in a more general circumstance, are the people who that strike is inconveniencing the actual ones who have the power to offer you better working conditions or salaries or whatever? I think that these strategic, can you actually make the world a better place questions should be in the forefront of protesters' thoughts about how to best organize and what strategies to take. I'm someone who doesn't get that interested in sort of the virtue signaling aspects of doing a protest. I do think that a lot of protesters are just there to sort of have their voices be heard, more so than to make the world a better place. I personally am about making the world a better place. So that's the balance that you have to strike. And I don't think I'm not sure that there is a simple set of rules you could hand down in a sort of bureaucratic way that would cover all of the cases. You have to think on a case-by-case basis what is actually going on. But the overall thing is I support the protesters. I support their rights to have their voices be heard. You know, I'm pretty much on one extreme when it comes to letting voices be heard, if that's what you're into. I think that you should let Nazis give talks on college campuses if they're invited by some legitimate college campus group. I think you should let people with all sorts of terrible ideas give talks and let them talk, and then ignore them if you want to. Give another talk if you want to do that, and then let people think about it. That's what I would think is the ideal situation. We can't always achieve it, but we can try to work toward it. That would be my goal. Mickle Pickle says, your recent guests have pointed to counterfactual reasoning as a key element of human advancement, either as mental time travel or considering the consequences of different initial conditions or empathy for the plights of others, etc. I've begun to notice how often I do it and to suspect it's true that educability, for example, and perhaps our overall success as a species depend upon it. However, I can't tell if it is required or most efficient or if it just happens to be what I personally do. How important do you think counterfactual reasoning is to effective prediction as individuals or to our past and future advancement as a species? It's hard to answer. I mean, the answer is super important, basically, but when you ask, how important is it, I'm not quite sure how to quantify it, right? But I do think that this idea of counterfactual reasoning, I think maybe the first time we talked about it was with Malcolm McIver, when he was talking about the initial evolutionary development of the capacity for counterfactual reasoning when fish climbed onto land and could suddenly see a lot further than they could before. And yeah, you're right. We've talked about people who have been thinking more specifically about how humans use those capacities. It's hard to imagine something. Oh, Carl Friston, we actually also talked with about that issue, because I remember joking with him that of my two cats, Ariel and Caliban, one seems to be capable of counterfactual reasoning and one does not. Caliban just seeks the local minimum. He just wants to be as happy as possible in the moment. I don't think the idea of other moments ever occurs to him. Whereas Ariel is the stereotypical cat who, when you open a door that she demands to have open, she's like, I don't know, do I want to open that? Do I want to walk to that threshold? I'm not quite sure. She's always thinking about the possible bad consequences, etc. And our feral cat, our outdoor cat Puck, who has hung around outside our yard for a while, he's super cautious, right? This is what is keeping him alive. So he doesn't do anything until he thinks about it 20 different ways. So somewhere that's close to when this capacity in some minor key was first developed evolutionarily. But anyway, yeah, absolutely possible, absolutely crucial, because I think that I suspect, and I'm just making stuff up, I'm not an expert on this, but I suspect that the parts of the brain that are good at, in general, abstract symbolic reasoning are either the same as or closely related to the parts of the brain that are good at counterfactual reasoning. I don't know if we've ever done a podcast on it, but back years ago, I organized workshops on the arrow of time where we were taught that you can do fMRI studies in the brain And you can show that when people think about possible future events, the literal part of the brain that is doing that work, conjuring up an imaginary hypothetical scenario, is the same part of the brain that sort of puts a scenario together when you're remembering things that actually did happen. So there's a sort of separate modules in the brain for storing information about what happened in the past versus literally putting on the show. You know, when we store the data of past memories, we don't store a videotape, we store something closer to a screenplay, and we put on a little show in our brains. And so that gives us a capacity to put on a hypothetical, counterfactual show. And I would not be at all surprised if that was a crucial step towards developing abstract symbolic reasoning, which is, of course, super duper important for everything that humans are able to do. It gives us that sort of Turing machine universality that lets us think about the universe in perhaps at least a maximally powerful way. I don't know the details. You should ask someone who knows about this stuff. Colleen Edwards asks, I asked this question on your quantum field theory thread regarding your upcoming book, which I know you still have to get to, but I just can't stand the anticipation, so I'll ask here in hopes of having an answer sooner. So what Colleen is referring to is that next week's podcast will be a solo podcast based on ideas from my upcoming book, Quanta and Fields, Volume 2 of the Biggest Ideas in the Universe. The idea of the book is to explain quantum mechanics and, more importantly, quantum field theory and particle physics in a way that is accessible to everyone, but that shows you the equations, right? That's the trick, and we'll see whether the trick works, but that's the goal in a short, powerful package. But there's so many ideas in quantum field theory. It's at the heart of modern physics that even in a solo podcast or a talk that I go around and give, I cannot talk about all the good ideas. So for Patreon supporters, I ask the questions like, what are the most important ideas you would like me to talk about? That is what Colleen is referring to about the quantum field theory thread. Just one of the many secret benefits of being a Patreon member here at Mindscape. Oh, I forgot to say, I got distracted by other issues. But of course, these AMA questions are supported by Patreon members, and they're the ones who get to ask them. If you would like to be a Patreon member, go to patreon.com/Sean M. Carroll, and you can see all of these secret threads and ask the questions also, as well as get advertising-free versions of the podcast. So Colleen goes on. As a non-physicist, I'd like to know, why does the field vibration change to a particle when it is observed? This concept is still tough for me to grasp. How can vibration change to a particle just like that? Is it possible to observe the vibration as it changes into a particle? So I think I will talk about this, hopefully. I do talk about it in the book in great detail, and I'll hopefully talk about it next week. But I think the rough thing to think is that it's not quite that a vibration is changing into a particle. The thing about quantum mechanics is that what you observe is not what is, right? If you think that what is the wave function of whatever things you're thinking about, what you see when you look at the wave function depends on certain observables. You see position, you see velocity. So forget about quantum fields. Even for an electron, if I have the wave function of electron, it could be spread out all over the place. And it's a particle, but it's a quantum particle, so it has no position. But I can observe the position, and I get an answer. I see, oh, there is a particle with a certain position. Or I can observe the momentum and see, there is a particle with a certain momentum. Can't do both at once because of the Heisenberg uncertainty principle. So the real question is, why, when we observe quantum fields, do we see particles? Why is it that the thing we observe looks particle-like? And so it's not that it transforms into it. I mean, it kind of does because wave functions collapse and that's how we talk about it, but it's not like it's doing it by itself. It's a function of that interaction. It's how you interact with the quantum fields that is making you see them as particles. And there's a longer story there, and it involves simple harmonic oscillators and things like that, but I'll just put a little tiny idea into your head to think about that will soften the journey to get there, which is, think about how electrons, particles, forget about the quantum field things, just think about how electrons have energy levels in atoms, right? The various orbitals that you study if you're a chemist. There's a lowest energy level, there's the higher energy levels that are sort of more funky looking orbitals and so forth. That gives rise to the periodic table and all that stuff. Where do those come from, and what is the role of these orbitals? You might say, well, look, I have a wave the wave function of the particle, and it's surrounding the nucleus of the atom. And I can imagine all sorts of profiles for the wave, right? All sorts of wavy kinds of things. But when you have the equation in front of you, the Schrödinger equation, what you find is that only certain profiles for that wave function have definite energies, right? There's a lowest energy answer to the question, what is the solution to the Schrödinger equation? And there's a discrete set of higher energy states. There's a discrete set of orbitals. So even though in principle the electron wave function can have any shape at all, in practice, dynamically, it goes to lower and lower energy states, and those energy states have definite shapes, okay? And the definite shapes they can have form a discrete set, even though the underlying wave is continuous. Much like, and you will hear this analogy again, much like plucking a violin string with its ends held down. There is a fundamental tone, and there are harmonics that have more vibrations in them, but they come in a discrete set. So the softening the blow kind of hint I will give you is quantum fields are also like that. Even though the quantum field need not be isolated around a nucleus of an atom or anything like that, it has vibrations that have definite energies, and there's a discrete set of them. And it turns out, I literally say in the book, it's a walks like a duck, quacks like a duck situation. The discrete energy levels that a quantum field can have turn out to have all the properties of particles, right? There's a state with zero energy, or the minimum energy state, which we interpret as empty space. There's a state with one quantum worth of energy, and you can sort of look at it from different reference frames, and it looks like it has momentum, and it looks like a one particle state. And then there's the next highest energy states that have at least twice as much energy. Why? Because they're interpreted as two particle states, etc. So it's a combination of those two things. Number one, solving the Schrödinger equation gets you these discrete energy levels that kind of have particle-like behavior. And then number two, when you observe the quantum field, you're generally looking for things that have some discrete amount of energy, some definite amount of energy, I should say. The wave function itself of the field might be a superposition of various different states of energy, just like a radioactive nucleus can be in a superposition of I've decayed and I've not decayed. But both of those are going to be things you observe. When you observe, you look for locations of things, and the locations, the sort of localized excitations, map onto these discrete energy levels, and we interpret them as particles. So it's really that they always are waves. They look to us as particles because of the dynamics of the Schrödinger equation applied to the quantum fields. Hopefully that's at least a little bit of help. Peter says, what's the update on your bold.org fund and scholarship? Do you have any specific goals relating to the number and amount of grants you hope to provide in the future? Overall, what was your experience with using that platform? So yeah, if you go to the webpage, preposterousuniverse.com/podcast, on the right-hand sidebar, there's a link to a bold.org Mindscape Big Picture Scholarship page. And we gave 2 scholarships last year. 2 scholarships the previous year, or I don't know, whatever that year was, and then 1 scholarship this year. And it was kind of my fault. We should have given away 2 scholarships this year, but I did the paperwork badly, or we didn't they have rules. Bold.org, which organizes things, has rules that say like you can't change the number or amount of scholarships in midstream. You have to say ahead of time how many scholarships you're going to give. So it was my fault not moving quickly enough on that. So I'm hopeful that next year we'll either be able to give away multiple scholarships or maybe slightly larger scholarships. Cannot say enough good things about you folks out there, the listeners here who have been donating to that scholarship fund in really just ways that warm my heart. It feels great that there's so much support out there. And the students are extremely appreciative of this. Again, I've not been very good at communicating with them, but they send me very nice thank you notes. And I'm very hopeful that we're helping some people who otherwise would find it hard to go to college and to do these wonderful things. So thank you all for supporting the scholarship. Alan White says, I understand that an electron is a wave in the electron field. I also know that if I solve Schrödinger's equation subject to some boundary conditions, I find a wave function for the electron that gives the probability of the electron's location. Are these two waves the same? Aha, yes, another good conceptual question that we will get to. The answer is no. They are not the same. Very briefly, I'll say this because I'll go into it in greater detail next week, but in quantum mechanics as it was first developed by Schrödinger and Heisenberg, etc., you start with a classical description of a point particle, call it an electron or whatever, and you quantize it. And there's different ways of quantizing things. In Schrödinger's way, you would replace the particle with a location and a momentum with a wave function that you could make observations of and get an answer for where position or momentum is. But the thing that you're quantizing is a particle. And then after you quantize it, it is described by a wave function. In quantum field theory, by contrast, whether it's a field theory of electrons or photons or anything else, the thing that you're quantizing is a wave, and then you quantize that wave. What does that mean? Well, just like for a particle, you assign a complex number to every possible position, and then that complex number squared is the probability that you observe it. Here, for a wave, for quantum field theory, you assign a complex number to every possible profile of the field. And so what you imagine you're observing, even though maybe it's not the actual observation that's easy to make, but what you imagine observing is the profile of the field all throughout space all at once. And then there's a wave function of the field. So that's like a waviness on top of waviness that gives you the probability of doing that. Now, the weird thing, as we just discussed, is that despite the fact that you start with a field and then you quantize it to get a wave function of that field, what it looks like after doing that are particles. One of the big lessons that I try to get across in the upcoming book, which is going to come out very soon, is that there's nothing intrinsically discrete or pixelated or lumpy or quantum in quantum mechanics. It is all continuous and smooth until you start asking about what we measure, what we observe, okay? And so it's weird. It's a weird fact. We'll try to explain it, how you start with a wave function, start with a wave, a classical field, construct a wave function of that classical field, and what you end up observing when you measure it are point-like particles. Just the miracle of quantum field theory. And if it bothers you for electrons, just think about it for photons, right? That's where the photoelectric effect and the blackbody radiation explanation that Max Planck came up with, etc., come in. Tiny vibrations in the electromagnetic field are observed as particles that we call photons, even though the electromagnetic field is certainly a field by itself, classically. Brian says, is there a way to get all the earliest Mindscape episodes on Patreon or commercial free? I only found them through your website and I really do not want to listen to them with the commercials. Yes, so we started Patreon later. There's two things going on here. One is that we started Patreon after starting Mindscape. So Mindscape started all by itself, and we started Patreon. So there were no ads at all on Mindscape to begin, but then, we got sponsorship and so forth, and they put ads in after the fact to the early ones. I honestly forget whether the various earliest episodes of Mindscape are even on Patreon, but there's a separate problem, which is that there are early episodes of Mindscape that are supposed to be on Patreon, which there's some technical glitch that erased them. So the blog posts are there, the entries, but not the actual audio files. And I've had ongoing discussions with Patreon back and forth, where they went, how to get them back. They can't seem to find them. I don't know what's going on there. It's not that many, but it's an annoying amount. So they said the only thing that I can do is dig up the original audio files and re-upload them. I have not yet done that. I've been busy doing other things. I really do hope to do that at some point. Keep bugging me about it. I'll try to get around to it. GS says, I've wanted to be a theoretical physicist studying the foundations of quantum mechanics since I was a teenager, but for reasons I won't get into, I ended up getting a degree in computer science and have been working in the tech industry instead for over a decade. I'm at the point in my life where I'm seriously considering going back to school to get a PhD and pursue a career as a theoretical physicist. This would be a long and difficult route, and it would be only worth it to me if I actually ended up with a job where I could do theoretical physics research as my day job. It seems to me that as private companies have no interest in theoretical physics, becoming a professor is the only way to do this, and positions are very limited. If this is correct, then the risk of having to return to my old job after all the work of obtaining a PhD is too high. However, I'm hoping there's some other career opportunities that I'm not aware of. My question is, do I have the right idea about how difficult it would be to get a job in this field, or are you aware of other career paths that would allow one to do theoretical physics research? Unfortunately, GS, I have very little good news for you here on either count. It is difficult to get a job in this field. If you go to the very best graduate schools, most people who graduate with PhDs doing theoretical physics from those graduate schools do not end up as physics professors. Many of them do. It's not like it's an infinitesimal fraction, but there's a lot of competition. It's the single biggest downside for me of life as an academic is that it's a constant series of competitions. And not because people are evil or like competition, but because there just aren't that many jobs out there. It's like being a professional musician or athlete or whatever. There's far more people applying for these jobs. There's no way around that unless society dramatically changes its allocation of resources and starts funding a lot more professors somewhere. So it is hard to get a job. And sadly, there aren't that many jobs outside academia. It depends on what you mean by doing theoretical physics, but particularly since you mentioned foundations of quantum mechanics, that's even harder than the average theoretical physics PhD. There are very, very few jobs in foundations of quantum mechanics. There are closely related areas in gravity, in quantum field theory, in particle physics, and what have you, but it's still a long road to hoe. So all of these, the thing to keep in mind is all of these considerations are considerations of probabilities. There's nothing you can do that makes you guaranteed to get a job doing theoretical physics or guaranteed to not get a job. There's always a chance. But like you say, there's not that many positions outside of academia, essentially none, and the jobs in academia are very unlikely. So I am a big believer in thinking about theoretical physics or even thinking originally about it and doing research in it, even if you don't have it as your day job. I think that that's something that everyone can aspire to if that's what they want to do. And I'm not saying don't go back to school and get the PhD. The PhD in physics, I think, is a very useful thing, no matter what job you end up doing. But we admit that there are realities. There's where you are in your life, what your income is, what your family situation is, et cetera. Perfectly valid to take those into consideration. So I wish I could give you better news than that, but I got to be honest about these things. Sean Khanna says, how often do you have to decline invitations for podcast interviews, et cetera? What criteria do you look for in a podcast before accepting to be interviewed? All the time I decline invitations. As you might guess, I get a huge number of invitations. It's pretty easy to start a podcast, pretty easy to find my email and ask me to be on it. And so I feel bad. I would like to do them all, but it's literally just a matter of constraints. Doing the podcast, doing Mindscape, is not my day job. It's not what I spend most of my time doing. And it could take over my life if I let it. So I have to be very, very disciplined, I suppose is the word, to keep the amount of time I spend podcasting in total to be very limited per year. And therefore, if I'm spending a significant amount of time on Mindscape, I'm not going to appear elsewhere as often. I appear much less on other people's podcasts now than I did before starting my own. So what criteria do I use? I mean, basically, there's no set list of questions or anything like that. But if I am personal friends with somebody, or if they've been on my podcast, et cetera, then I will probably go on. Or if I'm trying to promote a new book and they have a very big podcast with a very big reach, I will probably go on, or at least I will try to. That's about it. And, I even at that, I think that I'm doing more podcasts than I really should. Which is okay because there's other people out there who are super interesting to get on your podcast. If anyone's listening who is starting a podcast, interested in physics or philosophy or academia or ideas more generally, it would be terrible if every podcast was just podcasters interviewing other podcasters. That's very, inbred and stagnant. You want to interview people who haven't been heard that much. Now, I know that if you're trying to build an audience, getting big names on is definitely helpful. Getting people who have a podcast and therefore are recognizable to the podcast listening audience is absolutely helpful. I won't tell you not to do that, but I will advise not sticking to only doing that. And by the way, I don't mind getting invitations to podcasts as long as you don't mind me saying no. I'm happy to be invited. You never know. Maybe I'm in a soft touch kind of mood that day. George says, how did you come to believe in poetic naturalism? I'd love to hear a timeline of how your views on that reality, on what reality is, have evolved over time. I don't, I'm not very good at remembering exactly my own ideas about these kinds of things. So, as I've said before on the podcast, I remember where I am now, but I have trouble telling you exactly how I get here. This is why autobiographies are often not as good as biographies in some sense. But, I toyed with atheism and what I guess I would now call naturalism back when I was in high school without committing it to it seriously. It was in college that I became a fervent or, thoroughgoing atheist or naturalist. But I did have beliefs that I've since dramatically changed. I was a moral realist, for example. I had the simple-minded view that you could just treat maximizing utility or whatever as a scientific problem, or even that you could take, some criteria like survival of the fittest and turn it into moral principles. These days, with slightly better philosophical background, I know that that's not the case and you have to do better. Emergent levels being real. I'm not sure whether I should count mathematical objects as being real, but I lean toward no on that one. These are still developing over time. So I think that, probably, I don't know, when I really sort of started thinking of emergence in a serious way and therefore higher levels as having their own kind of reality. I was never against it, but I don't think I've ever really thought about it very carefully. Cheesy Klepna says, I have trouble understanding renormalization. Your video in the series The Biggest Ideas in the Universe was very helpful, but I still have many questions. One of them would be how legitimate, of a legitimate trick renormalization is. Are the infinities really predicted by QFT, and do we have to add another element to our theory to make answers finite? Or are they, for example, just a feature of perturbation theory, and when doing QFT non-perturbatively, they would disappear? Well, I hope that I think that if you watch the video that I did in the biggest ideas biggest ideas of the universe in the universe, you should know what my answer to this is, because I do think I gave it there, which is that until mostly when we're doing quantum field theory, we don't think that the theories we're working with are the final theory of everything, right? You should think of the infinities that we encounter in quantum field theory as placeholders for we don't have the final theory yet. Clearly, until we understand quantum gravity in the ultraviolet at high energies, we don't have the final theory yet, right? And therefore, the infinities that we get, which all come from looking at very, very short scales, very, very high energies, but ignoring gravity, kind of shouldn't worry you. I mean, that's clearly inconsistent, because when energies become important, gravity is going to become important when energies become high. So therefore, we should do what Ken Wilson taught us to do and cut off our theories at some ultraviolet scale, take whatever happens in that unknown ultraviolet regime, short distances, high energies, and bundle them up into their infrared effects and work with an effective field theory. If that was not clear in the video, then it will be hopefully super duper clear in the book, because I really pushed at trying to explain that. That is, to me, one of the single biggest lessons in studying quantum field theory, and therefore I talk about it a lot in The Biggest Ideas. There's a whole chapter devoted to exactly this idea. Mife, M-I-F-E, says, if we consider that atoms are in reality more wave-like than particle-like, is it incorrect to assume that during compression, such as in the formation of a black hole, particles simply come closer and stick together? Is it rather kind of a superposition of waves? It is very much like a superposition of waves. So people often ask this about, if there's some limit to how much we can fit into a region of space, given the Pauli exclusion principle, how can you make a black hole or something like that? But remember that the Pauli exclusion principle doesn't say that there's a limit on how many electrons we can fit into a region of space. It says no two electrons can have exactly the same quantum state. So I can have as many electrons as I want in the same region of space, but they will have different wavelengths. They will have different momenta. Every different mode in the electron field corresponds to a particle with different momentum and therefore different energies. And I can pile a low momentum electron right on top of a high momentum electron, no problem. So what happens in the field theory as the collapse happens and the density of matter becomes higher and higher is that the waviness of the quantum field underlying the electron becomes more and more important. It goes from being just one or two particles to being a superposition of many, many kinds of particles. Of course, we don't really know what happens for reasons that we just said. And we don't understand quantum gravity and therefore quantum field theory in the high density, high energy regime. But there's no reason to think that anything we currently talk about is somehow illegitimate or incompatible with what happens there. All right, I'm going to group two questions together, and hopefully it will make sense. Aaron Holder says, at the risk of violating the no special relativity paradox requirement, could you please explain the twin paradox? I've read too many contradictory explanations, and I am confused. Is it acceleration that causes the different experience of time? And Paul Soldera says, when talking to people about physics, the hardest concept to explain is spacetime. Do you have some intuitive way to describe spacetime that people can more easily grasp? For the latter question, for Paul's question, everyone's different. Everyone's going to have a different aha moment when it comes to understanding the nature of spacetime. I do think that many, many discussions of special relativity do a bad job by talking about things like length contraction and time dilation, because those are exactly sort of keeping the notions of time and space separate, but acting as if they're sort of weird and flexible and different than what you think that they are. That is very, very difficult for people to wrap their minds around. Space-time as a unified whole, once you take it seriously, I think is much easier to wrap your mind around than time dilation and length contraction. Really think in terms of space-time. And, when people say, what do you mean by space-time? I'm not quite sure what to say. It is both space and time. Is it a set of events, the set of places you can be in the universe indexed both by where you are and when you are? That doesn't seem that difficult to grasp at all. What is maybe difficult to grasp is the fact that they are unified together. And all that means is that in some very, very specific sense, there's no unique, preferred, well-defined way of dividing space-time into space and time. And I think that's pretty easy to understand also. Here on the Earth, we have put coordinates on the Earth, latitude and longitude. We put, so the 0 of latitude is at the North Pole and the South Pole, and we go from there, right? But everyone admits we could have put different coordinates on there. We could have rotated our coordinate system very easily. That's what happens in space-time. Choosing different ways of slicing space-time into space and time is exactly choosing a different coordinate system. So to Aaron's question, once again, I do recommend reading The Biggest Ideas in the Universe, Volume 1, because I explained this in great detail, or even for that matter, From Eternity to Here, where I explain it also. But the twin paradox is an immediate consequence of accepting the fact that the duration of time that you personally experience is a way of measuring the interval you have traversed through space-time. It is exactly the same as saying I have 2 points in space, and I can take the shortest distance path between them, a straight line, but I can also take longer paths. I can go on curvy paths. Nobody is surprised when two people go from the same point A to the same point B, but walk a different distance because they took different paths. That's all that's going on in the twin paradox. One twin stays behind and does essentially straight line motion through space-time, that is to say, not moving in space, only moving in time. The other one zips out and then comes back, okay? So that is a curved path through space-time. And the difference between space and time is that whereas in space, the shortest distance is the straight line, in time, the longest time is the straight line. That is the actual quantitative difference between space-like paths and time-like paths. So you can easily remember which twin is younger, because the twin that didn't move, the twin that basically moved on a straight line, maximized their time elapsed, and therefore the twin that didn't move will always be older than the twin that zoomed out and came back. It is not the acceleration that causes the different experience of time. It is the fact that one path is straight and one path is curved. Of course, the fact that one path is straight and one path is curved is because one accelerated. That is absolutely true. But you can have exactly the same amount of acceleration and very different path lengths depending on when those accelerations happen. It really is the length of the curve that matters. Christian Hoffman says, I've recently learned about spinors and the spin statistics theorem. Good for you, Christian. These are good things to learn about. In the few videos that I watched, they were regarded as rather mysterious, and Wikipedia says that an elementary explanation for the spin statistics theorem cannot be given. What makes the spin statistics theorem so mysterious, and why can't I have my elementary explanation? Look, I'm not someone who believes that every interesting fact has an elementary explanation. Sometimes we can really get insight into things, and it took us a long time to discover something, but after the fact, we can come up with some elementary explanation for it. Other times, we just can't. You gotta accept that. And one person's elementary explanation might not be another person's. I think with the spin statistics theorem, which, by the way, for those of you out there who don't know it, is a connection between the spin of various elementary particles and guess what? There's statistics, but statistics in this case mean, are they bosons, which means they like piling on top of each other. You can fit as many particles in exactly the same quantum state as you want, or are they fermions, which means that the Pauli exclusion principle, which we just talked about, holds, and you can only have one particle in each particular quantum state. So when we say bosons and fermions, you will often be told that bosons have spin 0, 1, 2, fermions have spin 1/2, 3/2, 5/2, etc. That is true, but that's not the definition of bosons and fermions. The definition is, can they pile on top of each other, or do they take up space? The spin statistics theorem tells us, as a theorem of relativistic Lorentz invariant quantum field theory, that the ones that have integer spins are going to be the ones that can pile on top of each other. The ones that have half integer spins are the ones going to be the ones that take up space. Now, I can give a hand-waving explanation for this, no problem. I do in, guess what, my upcoming book, The Biggest Ideas in the Universe, Volume 2, Quanta and Fields. And here's roughly the hand-waving explanation. It comes in 2 parts. Neither part will make sense by itself, but you have to read the book for that. Part 1 says, take a single spin 1/2 particle, for example, and rotate it by 360 degrees. Ordinarily, when you rotate something by 360 degrees, it comes back to where it started. But spinners, which are the mathematical description of electrons and other spin 1/2 particles, have this special feature that they pick up a minus sign when they come back to their original starting point after being rotated by 360 degrees. It doesn't matter, because what matters is the wave function squared, right? And so the minus sign doesn't really make any difference. Similarly, but not identically, if you have 2 particles that are identical and that are fermions, when you exchange them with each other, the overall thing picks up a minus sign. These are 2 different operations. One says I have a spin 1/2 particle and I rotate it by 360 degrees. The other one says that I have a fermion, that is to say a particle that takes up space. I have 2 of them and I interchange them with each other, 2 identical particles. But it turns out that those minus signs cancel each other out. They're basically the same minus sign in some very real sense. That is the origin of the spin statistics theorem. Now, very obviously, that's not a proof of anything. For one thing, the actual proof relies on relativity. And I didn't mention relativity there at all, right? So the spin statistics theorem is famously something where there exist hand-wavy discussions that make it plausible that it's true, and people often give those plausibility arguments, but the actual rigorous proof of it requires very, very delicate operations in relativistic quantum field theory. If you want those very, very nuanced, delicate operations to be made elementary, I'm not the person to come to. No, I don't know how to do that, and I don't know anyone who does know how to do that. Sorry about that. Richard Williams says, I recently told my 11-year-old about the people living on one of the Andaman Islands that didn't know about the rest of the world. He was shocked that it was actually illegal to try to visit or contact them. We both agreed that had we been born there, we would definitely want to know about the rest of humanity. I remember finding out at a similar age to him and also being shocked. Do you feel this policy is right? Is it analogous to the prime directive in Star Trek or the culture's contact rules? Now I'm older and can see the difficulties of any contact. I'm definitely torn as to what is for the best. So, by the way, explaining that little aside there at the end, the prime directive in Star Trek says that you're not supposed to meddle with the history of a pre-technological developing civilization. That's what the Federation of Planets is supposed to be doing. They violate it all the time, of course, to make the shows interesting. In Ian Banks's culture novels, it is very much the opposite. The culture is this vast pan-species civilization that is constantly meddling with other pre-technological civilizations to try to make them develop more peacefully, et cetera. So it's not as if everyone agrees on what the right way to do things are. I think that the right answer here would be you should ask them. You should ask these people, do they want to be contacted by the outside world? Of course, the tension there is that it's hard to ask them if you can't contact them. My impression, and I don't know a lot about this, I just remember sort of reading about it years ago, is that this particular tribe were contacted by, another tribe who did know about the outside world and were asked, do you want to be part of this global world? And they said no. So if that's true, then I'm 100% behind in agreement with what exactly happened there. But I don't know if it's true. I think that you should. I'm agreeing with your intuitions, I guess, or your inclination, which is to try to give them a choice. Don't just think to ourselves that we know what's best for them and what's best for them is not to know about us. But if they don't want to be contacted, then that should absolutely be their right. Or they just want to be left alone, that should be their right, even if we think they might be making a mistake. Sheldon Sillyman says, I'm currently reading The Disordered Cosmos by Chandra Prescott-Weinstein. It describes the walls that have always been in place to hinder and prevent anyone other than white males from becoming physicists. Do you see significant changes now, and what is being done to encourage diversity in professional physics circles? Well, I think that there are changes. I don't think the changes are specific to physics in particular. I think there are changes in the broader culture. People are much more conscious of the existence of discrimination now than they were before. There are still racist and sexist people out there, no doubt about it. I think that much of the problem comes from people who are racist and sexist and don't know it, who would swear on a stack of Bibles that they were not racist and sexist, but in various ways that they might not even themselves be aware of, make life harder for people who are in minorities of various sorts. But we are making progress, and it's because the people who have been discriminated against have raised a ruckus, and that makes the problem more obvious. And so there's more. I think that the default these days is to try to be very sensitive to those issues. Doesn't mean we always succeed. So I think it's getting better. If you just look at the numbers, it's still a long way from being equitable right now. And by equitable, just so I don't think there's a lot of trolls listening to this podcast, but there are some trolls out there. I don't care what the final percentages are. I don't insist that we be 50% men and 50% women in our field or whatever it is. Who cares? I don't care about that. What I care about is that everyone who wants to do it be given a fair shake. And right now, the percentages are overwhelmingly in favor of the white men. But that's not the point. The point is the reason why that is true is because there's a lot of barriers, a lot of walls up there for people who are not white men. And I think that it makes perfect sense to actively try to tear those walls down and restore some equitability. Sean Perry asks a priority question. Remember, priority questions are granted to Patreon supporters. Once in your life, you're able to ask a question that I will definitely try to answer. Most of the questions that are asked I can't answer. There's just too many of them, but priority questions I will always try to get to. So Sean's question is, location, size, and energy requirements aside, in theory, could a device create a micro black hole as a means of storing information for an albeit short period of time? And could that information be read by collecting all of the Hawking radiation as it dissipated? Could the storage capacity be calculated, and what would be the fidelity of the information read with respect to its original state? Will this be the new form of data compression on the quantum internet in a billion years? So I can pretty confidently say, no, this will never be the correct form of data compression. If you believe that information is conserved, then indeed the information that you put into a black hole will eventually come out. However, note two things. Number one, at a practical level, it comes out very, very, very slowly, right? Typically, well, let's just say a long time. I don't want to estimate because it depends on the mass of the black hole and things like that. For astrophysical black holes, it is a very large number of years. But more importantly, it's scrambled. It's completely in its least accessible form, that information. So it's absolutely not how you want to store the information. It's just a potentially possible way of doing it. I should also say I don't know whether or not it's even possible in practice to get the information out. Getting the information out means measuring the system, right? Measuring the radiation that comes out of the black hole. I presume that there are ways of doing that measurement that give you enough information about what went in that you could be useful to you, but I actually don't know that for sure. Information is lost when you do a quantum measurement. That's something we understand very, very well. Okay, The Great Deceiver says, here is a quote from one of my favorite philosophers, Alan Watts. If this is the way things started, if there was a Big Bang in the beginning, you're not something that's a result of the Big Bang. You're not something that is a sort of puppet on the end of the process. You are still the process. Now, maybe that's a bit of an obvious simplistic idea, but his point is that when we define ourselves as separate individuals, we cut ourselves off from the original force of the universe, which has many negative or far-reaching consequences historically, sociologically, and psychologically. What truth is there in that, do you think? Is it an important realization to be aware of as a scientist? Yeah, yes and no. I'm not sure about this one. We're absolutely part of the universe, right? That no one believes that more than naturalists do. We are made of the same kind of physical stuff. Physicalists, maybe I could even say, the same kind of physical stuff arranged in patterns that obey exactly the same kind of laws of physics as anything else. Literally, the atoms that are in your body don't stay in your body forever. They can be swapped in and out for other atoms, and you're still you because you are more of the pattern, the process, as Watts says. What is the implication of that, though? Like, what does that mean for your life? I don't think it means too much. I think that he is trading off of some kind of feeling that if we are part of the bigger process, we should literally feel a connection to it in some direct way. I'm not exactly sure what he's trying to get at. That's one of the benefits of speaking poetically is that people can find it hard to pin you down, and you can always have plausible deniability. But I'm not sure what that connection is. I mean, if every human being were literally different, were made of different kinds of materials and did not start from the same point as other things in the universe did, would that mean that I didn't need to care about them or take their feelings into consideration, or that I couldn't learn from talking to them? I don't think so. I hope not. I think that there are other reasons, mostly, to care about the rest of the universe other than we obey the same laws of physics and we're made of fundamentally the same stuff. Edward Sackinger says, I enjoyed reading your book, The Biggest Ideas in the Universe, Space-Time in Motion, and I'm looking forward to the next volume, Quanta and Fields. My question is about the Schwarzschild solution. Naively, it seems to give the space-time metric around a point mass, but you say in the book that it is the solution to Einstein's equation in empty space. Why does the mass at the center not count? Yeah, this is a very good question. This is something that maybe I should have said more clearly in the book, because once you come across that question early in your physics career, you sort of understand the answer to it and you forget that it was a question. But Schwarzschild's original idea was literally to imagine something like the Earth, not even a point mass, but something with some spherical symmetry, okay, but maybe finite radius, and think about the metric, the solution to Einstein's equation, outside of the Earth, okay? So when we say the solution in empty space, we don't mean it doesn't matter that the Earth is there, because the Earth provides the boundary conditions. Many times when you have differential equations, like Einstein's equation is, you can solve it in some region once you are told what the conditions are on the boundary of that region. So here we're solving it in empty space with the boundary condition that somewhere inside a spherical region that we are removing from consideration, there's a boundary condition reflecting the fact that there is a planet there or a star or whatever. So that's what we mean by solving an empty space. We're not solving the metric inside the Earth or inside the sun and so forth. Now, there's another thing that happened that Schwarzschild did not anticipate, which is that the actual solution does not describe a point mass. It just doesn't. It describes a black hole if you go inside, and a black hole has a singularity that is not a point in the middle. It is a moment in the future. It is a moment that you necessarily hit if you enter that event horizon, but that's a higher level, more complicated question. The point is that the reason why we say empty space is because we're thinking about the region outside the gravitating body. Jonathan Bird asks, who is your biggest inspiration as a bass player? Well, I have to remove the word inspiration really from this question, because even though I own a bass guitar and I occasionally fool around with it, I am in no sense really a bass player. So it's not like I am emulating the style of anybody else. I'm just not that good at it, okay? But I like different bass players of all sorts. My sort of rock and roll favorite bass players are kind of the standard people, John Entwistle is definitely one of the best. My progressive rock guys, Chris Squire, Geddy Lee, more jazzy people like Jaco Pastorius, more modern people like Flea, for example. And there's also, of course, a whole bunch of great jazz bass players, Charles Mingus and many others, Charlie Hayden, which that always makes me think when I think of, Charles Mingus as a bass player versus John Entwistle as a bass player. Like, it almost seems like they're playing different instruments, right? And of course they are, because Mingus is playing an upright acoustic bass and Entwistle is playing electric bass, but we still say they're bass players, but it's a very different kind of thing. It reminds me of a clip I once saw on YouTube of Keith Emerson, the rock and roll keyboard player, who had very eclectic tastes in music, and he would play classical and blues and jazz and whatever. He would play anything, and he pioneered a certain kind of rock synthesizer playing that is still heads and tails. No, many leagues above anyone else, I think, in the rock and roll keyboard playing space. But he once went on a TV show hosted by Oscar Peterson, the great jazz piano player, and they played together. And, Keith played some of his stuff, but then the two of them sat down and did a duo performance where they were improvising jazz. And I honestly say I felt bad for Keith Emerson because, if you were listening to them play and kind of thinking of it as jazz piano, Oscar Peterson was kicking his ass. He was many, many light years better than Keith Emerson was at this particular skill set. I don't really blame Keith for that. In fact, I give him credit for going to that situation because this was not his bread and butter. This was not what he was trained to do. His playing was much more on the beat, sort of direct and straightforward, whereas Peterson is kind of swinging and playing around with it and being more jazzy in various ways. But Keith had the courage to go up there and do that. I'm not quite sure how it would have fared had you given Oscar Peterson a Moog synthesizer and asked him to play something from Tarkus or something like that. But anyway, the point is, even saying the word bass player, just like saying the word keyboard player, can be almost completely different job descriptions. Rich LP says, I came across your summer book talk in my area for Quanta and Fields while perusing the list of upcoming events at one of my favorite local comedy clubs. I really enjoyed the talk you gave on Einstein's real equation for Volume 1 of The Biggest Ideas in the Universe. Can you tell us a bit about your upcoming book talks and any hints as to what this next book talk will cover? Well, I think podcast listeners will get a preview because I think that the solo podcast coming to advertise the book will cover some of the same ideas. For a talk, I don't have as much time, and in a talk, so you should aim for under an hour for the talk because there's always things that will drag you on, and you want some time for questions and things like that. Whereas in the podcast, I can go forever. But also in the talk, I have visual aids, right, which is hugely helpful. So the talk might be more comprehensible in some ways for that reason, but it will cover less stuff. So I'm still not sure, even though the clock is ticking, I'm not sure exactly how best to optimize those things, what I will cover in the podcast, what I will cover in the talk. Certainly, I want to cover this very basic question, why, when you start with a theory of fields and you quantize it, you get something that looks like particles, okay? I think that's the one thing that is very rarely talked about and people are curious about, okay? Beyond that, there's one direction to go in would be to talk about effective field theory, normalization, and interactions and so forth. A completely different direction would be to focus on symmetries and symmetry breaking and confinement and phases and things like that. A third direction would be to do spin statistics and stuff like that. Like any one of these is an hour-long talk, right? Once you add on the basics, intro stuff. So I'm not sure. Tune in, come. I haven't actually, the clock is ticking once again, but I need to update my website where I will do that, and then you will find a list of book tour events. There are not that many of them. I'm not flying around the country. This is a book tour up here in the Northeast where I can hop on the train, and it's not, it's a low budget book tour, let's put it that way. Roland Weber says, my local bookstore has 2 editions of The Biggest Ideas in the Universe, Quanta and Fields in the catalog. One gets published on May 14th by Penguin in the US, the other 2 days later and with a different cover by One World in the UK. I assume the content is identical, but can you tell us something about the differences? Did the US publisher insist on a head start and or a distinct cover? Yeah, so the way it works, just to fill you in, is if you, I can only say the way it works for me, okay? Other people will be different. I live in the United States. My agent and my publisher are all in the United States. So all of my negotiating and writing and editing is with my US publisher, who is Dutton, which is a part of Penguin. And we do all that, and it's a lot of work. So, the editors at Dutton help me write the book and, make suggestions and stuff like that. It's all a very important part of the process. And then they come out with a version of the book. But the way that they write the contract for the book, they do not insist on the rights to publish it outside the US. So the agent separately sells the rights to the UK, for example. And maybe, I don't even know, but I think that the UK publisher will also sell it in Canada and Australia and Commonwealth nations, maybe. I don't even know the details. But so One World in the UK has been publishing my books for a while now, and they do a great job, but they're not involved in the editing process, right? So basically, we send them the finished book, and then they come up with their own cover. And I forget, this is embarrassing, I should know. The question is always, do they anglicize the spellings of the letters in the book, right? Do they put a U in the word favorite and things like that? I don't think that they bother to do that these days, but some publishers will, I think. Anyway, they're polite enough to tell me, like, here's the cover we're going to use, but I don't have a lot of say. Like, as an author, you don't have that much say over the cover of your book or even the title of your book. You have say to the extent that they will politely ask you your opinion, and you can give your opinion, but it's sort of their choice at the end of the day. So happily, I've been pretty happy with the covers for my books. I do think The Big Picture had a cover which was not quite what I wanted, but my other books, and actually Particle at the End of the Universe was a weird cover, but that was just because they were rushing to get it out, and they did a wonderful job of getting it out in such a short time scale. But The Biggest Ideas in the Universe covers, I think, are great. Miles Jenkins says, in the February AMA, you were asked how you thought complexity emerged in the universe from the known laws of physics. I was surprised that you rather shrugged and said you didn't know, and made it sound like this was a new and challenging area of investigation just getting started. I had thought that the thermodynamic basis of the formation of complex molecular structures, as explained by former Mindscape guest Jeremy England, was fairly well established. That is, in my own understanding, in an open thermodynamic system, like the surface of the Earth, where septillions of atoms and molecules collide more or less at random and with varying levels of energy, sometimes old chemical bonds are broken, sometimes new bonds are formed. But any molecular structure whose formation in such a collision entailed the dispersal of some amount of energy as heat is less likely to be reversed by a subsequent collision in proportion to the amount of energy dispersed. Thus, there's an evolutionary direction, a kind of survival of the dispersingist that conduces to the formation of ever more complex structures. So the point, Miles, is that everything that you said is 100% completely correct up until the last half of the last sentence. Absolutely, in a environment that features dissipation and increase of entropy, structures will go down to lower energy states as they emit photons and heat and basically radiate out of the universe. But there's no guarantee that those lower energy structures are somehow complex. That's the whole point. Why is it that they become complex rather than simple, right? You can easily invent toy models where entropy increases and everything remains perfectly simple all along the way. You can invent other models where complex structures grow for a little while before, by the way, eventually disappearing again. If you continue to increase in entropy, all the complexity goes away. So the reason why it's an interesting open challenge is because complex structures are temporary steps along the way from low entropy to high entropy that may or may not be reached. And so there's a very good question, under what conditions are they reached? Are there some overarching rules about why they're reached, how they're reached, all the stuff like that? So there's a long way to go to completely understand this. Sandro Stuckey says, does the quantum vacuum state in a quantum field theory have dynamics that could lead to many world style branching? I've heard I've heard people say that something could fluctuate out of the quantum vacuum, but I don't understand if such fluctuations could give rise to structures that last over time. Interestingly, this is not known. That is to say, sometimes I say things are not known. What I mean is there are people out there who think they know the answer, but there's other people out there who think they know the answer, and they're both perfectly respectable people, and they completely disagree with each other. So as a field, we physicists do not agree on this question. Are there dynamical fluctuations in the vacuum state of a quantum field theory? I just gave a talk on it actually a couple months ago. There was a memorial workshop in honor of Jim Hartle, who passed away last year. Jim, with Murray Gell-Mann, developed the Decoherent Histories formulation of quantum mechanics, which I don't think is a separate interpretation or foundational theory of quantum mechanics. It is a tool that you can use to analyze what is basically the many worlds interpretation of quantum mechanics. But anyway, Decoherent Histories has this goal of thinking about the set of things that happen in a quantum state in terms of the histories of things over time and whether or not you can divide the evolving wave function into different histories that decohere from each other. And I wrote a paper with Kim Boddy and Jason Pollock about Boltzmann brains fluctuating out of the quantum vacuum. And we said, if you have truly reached the quantum vacuum state, not just approximately there, but truly there, then that state is static. Nothing happens in it. It is the same state from one moment to another, and therefore you should not say that dynamics happens in that state. And in particular, you should not say that things fluctuate into existence out of that state. So not everyone agrees. Seth Lloyd wrote a paper thereafter saying, I don't agree. I think I can start with a static quantum state, and I can find a set of histories that in the decoherent histories formalism will decohere from each other. And so my point in the talk that I gave, and this I'm not the first person to say this, but I tried to say it clearly, is that is too loose of a criterion, the ability to find some decoherent histories, because you can always find many, many, many different sets of decoherent histories representing very different things. And in the decoherent histories formalism, you can attach relative probabilities to the different histories within the set. But if you then pick a completely different set of histories, you cannot compare which set is more likely than the other. They both really exist at the same time. And so I think you need more stringent criteria for saying that a dynamical fluctuation really happens. And this is a quintessentially natural philosophy question. It's a question that requires input from philosophical thinking as well as from physics. So my answer is no, there's no dynamics in the quantum state, but other people disagree. If I can find the time, I will take the talk that I gave and write it up as a real paper, and I will let you know when that happens. Eric Dovigi says, according to the many worlds interpretation of quantum mechanics, is there an exact Lord of the Rings world out there? Is there a Star Wars world except Darth Vader loves to sing? In other words, what kinds of possibilities are we allowed to consider and what kinds are we not? So the direct answer to the latter question, which is not exactly the same as the former question, is we consider in many worlds what happens in the Schrödinger equation. The Schrödinger equation tells us that there's a wave function that evolves over time. And then you can ask how I can divide that wave function into a set of decohered, non-interacting worlds, and those are the worlds that happen. It is nowhere close to saying everything happens. It is what is predicted by the Schrödinger equation. That is what happens. Now, it is possible, by the way, certain things certainly cannot happen, and it's obvious that they won't happen. If you have a spin of an electron that is 100% in the spin-up state, then it is not going to branch into spin up plus spin down. It's just spin up. That's all that there is. There's zero probability that you're going to observe it to be spin down. So that is an example of something that wouldn't happen in the many worlds interpretation. More robustly, there are conservation laws, like conservation of electric charge, that are not violated in many worlds. You will never see charge popping in and out of existence. But it is conceivable, I think that the details matter here, I'm not going to promise you that it's true, but it is conceivable that very, very weird-looking things will happen in one branch of the wave function that resemble Lord of the Rings or Star Wars or whatever. in exactly the same way that when I put my coffee mug on the table, there's a chance that it will quantum tunnel through the table. That chance is super, 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 super duper low, and therefore we don't think about it and worry about it. But maybe you could argue that in many worlds, there's a world in which it happens. And these fantasy worlds can be thought of as concatenations of many, 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 many super unlikely events. But I will, even if that's possible, and I'm not saying it is possible, I'm saying it's conceivable. I'm saying I don't know because you'd have to go through the details of seeing, is there a decoherent branch of the wave function in the universe that looks like that? And I don't know the answer. But I would strongly, strongly advise not to worry about it. I think this is a weird thing, and this goes beyond Eric's question, but it is a weird thing when people come across the many worlds interpretation of quantum mechanics. They begin to fret about the super duper unlikely worlds. And I think that one of the major sort of mental stumbling blocks about people accepting many worlds is just that the people who like many worlds, like myself, I don't care about the worlds. The worlds are not the point. That's like they're a byproduct, right? Hugh Everett was not trying to put in all of these extra worlds into quantum mechanics. The worlds were already there. They were there in Hilbert space. They were there once you imagine you have a wave function representing a superposition of different possibilities. All Everett says is that you don't have to get rid of them to understand what the theory predicts, and it predicts exactly what we see. But the worlds are not the point, okay? Even the likely worlds are not the point. The point is what we observe in our world, and that this very simple underlying structure helps us understand and explain what we see in our world. And when it comes to the super duper unlikely worlds, they are there in exactly the way that the entire text of Lord of the Rings is somewhere to be found in the digits of pi, right? If you keep writing out the digits of pi and it's a truly random number, then somewhere you're going to come across the exact text of the Lord of the Rings. Very much like Borges's Library of Babel, right? The problem, as you know from thinking about that example, is that you also come across a huge number of things that are almost like that, but not quite. And how do you know whether you're in the right one or not? And furthermore, you have to look a very, 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 very long time to find any of them at all. It's not relevant. It's not important. These worlds, even if they're there, their probability that you would, by self-locating uncertainty, find yourself in one is so incredibly low that you can just ignore it. Trust me, you can just ignore it. Astro Nobel says, in the big picture, you write that the absence of consistency across sacred texts counts as evidence against theism. Following the same reasoning, we can notice that mathematicians all over the world, provided they are not making obvious mistakes, eventually will all agree about mathematical theories. Would that then not be a strong evidence in favor of mathematical realism? Well, it's some evidence in favor of mathematical realism in the following sense. If you noticed that mathematical texts across the world were inconsistent with each other, you would, I think, quite rightly take that as evidence against mathematical realism, right? Therefore, the fact that they are consistent is certainly evidence for mathematical realism. But, excuse me, it is not strong evidence for mathematical realism. And the reason why it's not strong evidence is because it's a different kind of question. The question about whether God exists or not is fundamentally an empirical question in the sense that there are different possible worlds, a world with God, a world without God, and we are trying to decide whether or not we live in one world or the other, but they're both physically imaginable kinds of worlds. People who believe in mathematical realism don't think that there are possible worlds in which mathematical realism is true and others in which it's not, right? They think it's a matter of principle. They think it's sort of an ontological, metaphysical, basic feature of mathematics that it is real. So the question of mathematical realism is just not analogous to the question of theism versus atheism. So it's not nearly as relevant, this little piece of evidence that you bring forward. Ilya Lvov says, could you please explain the motivational thought behind your recent overlapping degrees of freedom paper? While there are a lot more almost orthogonal vectors in an n-dimensional Hilbert space than strictly orthogonal, surely it's still a finite number. How does it help reconciling such a Hilbert space with the uncountable dimensional Hilbert space of quantum field theory? So Ilya is referring to a paper that collaborators and I, Oliver Friedrich in particular, just published or just put on the archive. We haven't yet published it yet. Still waiting for that referee report to come in. But we're trying to reconcile the limit on the number of quantum states in a region of space-time from the holographic principle with the counting that you would get from quantum field theory. And we point out that you can fit a lot of almost orthogonal but slightly overlapping states into a vector space, and therefore maybe that's what's going on, that the quantum field theory states are in fact not quite orthogonal to each other, so we think there are more degrees of freedom than there really are. But the question is, if you think that the quantum field theory is infinite dimensional, surely you can't fit all of them. That's completely true, but we don't think that. So the starting point for the kind of quantum field theory description that we're comparing our holographic description to has a bunch of cutoffs on it. You have a region of space, so you fix the size of the region. That gives you an infrared cutoff, a long distance cutoff, the size of the region. You put an ultraviolet cutoff on, you put a short distance cutoff on because you say that we're not looking at vectors or at wavelengths smaller than the Planck scale. And you also have an energy cutoff. You do not consider states that have so much energy that you make a black hole, because that is a feature of quantum gravity. So once you do all of these cutoffs, you're not strictly dealing with a full quantum field theory. You're dealing with a truncation of quantum field theory that has a finite dimensional set of vectors. But that's still, those vectors, that set of vectors is still more than you would get from the holographic bound. So that's why you want them to be slightly overlapping. Mike Pencil says, which of the following would you like to experience in your lifetime? A 4K photograph of a black hole, the discovery of a single-celled life on another planet, finding the dark matter particle, or the Sixers beating the Celtics in the playoffs? I'm torn here. I mean, there's two obvious choices, discovering life or the Sixers beating the Celtics. So I'm wondering, if I choose the single-celled life, does that mean the Sixers never beat the Celtics in the playoffs? That would be very, very sad to me, because I think that the Sixers beating the Celtics in the playoffs is something I am likely to see sometime in my life going forward. Maybe I'm wrong. Famous last words. But okay, anyway, to the more serious ones, I think that discovering single-celled life on another planet would definitely 100% be the easy choice here, because it's a different kind of thing. A photograph of a black hole is great, but I think I know what black holes look like, so I'm not expecting surprises there. Finding the dark matter particle has greater chances of being a surprise, because even though we think we know that there's dark matter, we don't know what exactly it is. So finding which particular kind of particle it is would be very educational. But still, we have a lot of good candidates for what it could be, and finding that it was one of those candidates would be very, very interesting. But okay, then we guessed right. Somebody guessed right. Whereas finding life on another planet, of course, people have proposed that that's true, but what kind of life is it? There's an enormous amount to learn from doing that. Just learning the fact that life is not so rare that it only exists here in the solar system would be enormously, enormously educational to us. So finding a single-cell life anywhere else in the universe would be far and away, I think, the most exciting and interesting result there. I'm going to group two questions together. One is from Peter Gaffney, who says, if space is expanding, is time also in some sense expanding? And what does that mean? And Christopher Burke says, I hear about the universe expanding in the spatial sense, not in a relativistic sense, but in that distances between objects are getting bigger. One of the issues discovered from the cosmic microwave background was that normal expansion wasn't enough to allow for the uniformity of the universe, so inflation is the current solution. My question, has the expansion or contraction of time been considered in addition to or instead of inflation? The idea of the initial phase change was time. Why wouldn't this work? So both questions are in some sense saying, can time change or expand as well as space? But the answer is no. That's an easy question. It can't expand in the same space and in the same sense as space is expanding. And, I'm going to give into the temptation to give the glib explanation of that, and then I will try to amplify it a little bit. Look, what do you mean by expand? When you say space is expanding, you mean that the distance between galaxies who are far away from each other is getting bigger as a function of time. That's what it means. So what would it possibly mean for time to expand? How can time change as a function of time? Time always travels at 1 second per second, okay? So there is no room in the description of what you mean by time for it to expand in the same sense that space does. In yet other words, there are different ways to measure time, but they're consistent with each other. If you move on the same kind of trajectory through the universe and you measure time with an hourglass and a ticking clock and your heartbeat and whatever, to the extent that your instruments are accurate, they will always give you the same answer. So that's what it means operationally to say that time ticks along at 1 second per second. At the mathematical level, if you know general relativity, this is immediately obvious, this question. You just write down the metric of an expanding universe, or expanding or contracting, it doesn't really matter. And you could choose, there's a part of that metric tensor, the thing that tells you the geometry of space-time, that tells you the rate of the time coordinate passing as opposed to the proper time of some observer. And of course, the time coordinate can pass at whatever time you want. Coordinates are arbitrary. You can make them up. But you immediately notice that I could change variables to use the proper time of an observer as my time coordinate, and then time cannot expand. What can happen is that the coordinate time can have a different relationship to proper time of observers as a function of space, as a function of where you are in the universe. That's why you get things like gravitational time dilation in black holes and things like that. But time itself expanding is kind of a non-starter as a concept. Chris Gunter says, what is a scalar doublet and how does it differ from a vector in a two-dimensional abstract space? So this is a technical question that I'll answer very quickly. Again, read my book coming out just next week, Quanta and Fields, goes into this in great detail. The Higgs boson field that you will read about, if you know about the Higgs boson, the field before spontaneous symmetry breaking is described as a scalar doublet, a complex scalar doublet. What that means is there are two scalar fields, and they're related to each other by some symmetry transformation. Indeed, the symmetry is labeled SU2. That is the SU2 that appears when people say the standard model is an SU3 cross SU2 cross U1 symmetry group. And so, yeah, it's a vector in an abstract two-dimensional space. It is exactly that. It does not differ from that. It's just that when you have a group like SU2, you can have different representations of that group, right? So just a little while ago, when we were talking about spinors and the spin statistics theorem, we mentioned that the electron's wave function has the feature that if you rotate the electron by 360 degrees, it picks up a minus sign. The Higgs boson's wave function has the feature that if you rotate it by 360 degrees, it stays exactly the same. It doesn't change at all. So there's the same symmetry group, rotations in three-dimensional space, but fields behave differently under those symmetry groups, and that's called different representations of the group. So the reason why we use language like scalar doublet rather than just saying this has an SU2 symmetry is because the SU2 symmetry can be represented in different ways. A doublet, a two-dimensional vector, is just one such representation. Shambles says, from what I see of the effective altruism movement, I'm not really seeing anything more effective than old-fashioned charity, directed at negating immediate suffering of crises. To be truly effective, surely it needs to be addressing climate change and global poverty, which the movement seems keen to shy away from. Would love to hear any thoughts you have about it. So my foremost thought, there's two foremost thoughts I have about effective altruism. One is the idea is a good one. The idea as stated, that if you want to be giving money to charity, to be thinking altruistically, it makes more sense to do some cost-benefit analysis and to figure out where your money or your donations can do the most good. I don't see how you can argue with that. You might choose not to actually take that path. You might prefer to give to your local cat shelter rather than to sending malaria nets to Africa. That's perfectly okay, but knowing what the most effective way to alleviate suffering would be sounds like a good thing. The other immediate comment is that the fact that it's a movement is bad. I think that there are ideas that movements can take up or not, but you have to keep the idea separate from the movement that is trying to put that idea into practice. And I think that in the case of effective altruism, number one, those lines are blurred. The people who are thinking about the ideas think of themselves as part of a movement. And number two, they have therefore empirically fallen into the trap that movements fall into, where they sort of become corrupt and go south, right? And that's why you get effective altruism getting mixed up with people like Sam Bankman-Fried, who built a lot of people out of money because they, went away from the idea of just making charities more effective and started thinking exactly along the lines that you're talking about, thinking more globally. But rather than thinking about climate change and poverty, they started thinking about existential risks and artificial intelligence taking over the world and things like that, more science fiction-y kinds of things, and came up with ex post facto rationalizations of some really bad behavior. So, look, I think it's perfectly okay to think about these bigger picture worries. And it's perfectly okay to think about the threat of AI or other existential risks. Also perfectly okay to think about climate change, global poverty, et cetera. That's not instead of eliminating poverty or handing out malaria nets or giving shots to people in poor areas. You can do all of those things. This is why I'm not a utilitarian. I do not think that the right way to do things is just to find the one way to maximize utility and just do that, right? I think that doing lots of good things is actually having a pluralistic, rich ecosystem of good things being done is ultimately better, morally superior. Kevin James says, in your April AMA, you described spin glasses, and it reminded me of the resonance of molecules with aromatic rings, such as benzene. Is this perhaps a good real-world example of that sort of system where it is trying to achieve the lowest energy state? I mean, roughly speaking, no, it's not, because lots of systems that try to achieve a lowest energy state, a spin glass is enormously more complex than a single molecule with an aromatic ring, such as benzene. The fact that it has many sites with spins, and the spins have different kinds of couplings to each other, enables that complexity in a very specific way. That's where the interestingness and uniqueness of spin glasses really comes from. Whereas a single ring of benzene has a small number of particles, relatively speaking. Murray Dunn says, in a long ago AMA, you were kind enough to answer a question by explaining that the charge of a closed universe must be zero because all electric field lines must close. Through similar logic, is it possible to say that in a closed universe, all photons that are emitted must eventually be absorbed? Nope, it is not. In a closed universe, photons either are absorbed or they travel on forever. In a closed universe, both are possible because a closed universe just has a spherical topology, maybe. That's one example of a closed universe. It could have a toroidal topology or whatever. And there's no obstacle to the photon just going around the circle or the sphere or the torus many times. So no, it's not quite an analogous case. The photon, let's put it this way, the photon is traveling through time as well as space, whereas the electrical field lines stretch through space at every moment of time. Dazad says, Dazad wrote in terms of Maxwell's demon, but I think it was really Laplace's demon who was intended. So I'm going to replace that by saying Laplace's demon, even if supplied with full information about the current situation of every particle in a system, would presumably need to solve the three-body problem to be able to determine the future or past states of all but the simplest systems. Does this in any way undermine the usefulness of Laplace's demon as a thought experiment? No, it does not. Because a three-body problem is chaotic, which means that small errors in initial conditions can lead to large differences in final states. But the entire idea of Laplace's demon is that there are zero errors in past states, and there's zero errors in the calculation of how the things evolve forward. Look, Laplace's demon doesn't exist. There is no Laplace's demon. It's just a metaphor for saying the universe is deterministic and conserves information. So don't get upset if you think that no thing other than the universe could do this calculation. It's just really the universe. Think of Laplace's demon that way. Domino says, how can we tell that a photon has been redshifted versus simply having a lower energy level or just being red in the first place? Well, that's a good question. I mean, in principle, you can't. If you just had one photon that came from something you didn't know anything about in the universe, you wouldn't know what its initial redshift, or what its initial wavelength was, and therefore what its redshift had been. What you're looking for is many photons from a source so that you can single out spectral lines. The nice thing about quantum mechanics is that electrons in atoms have discrete energy levels. We can calculate what they are. And therefore, if you have a known atom, whether it's hydrogen or anything else, and a known transition, let's say between the lowest energy state and the second lowest energy state, you know exactly what the energy of the photon was, and therefore its wavelength at the moment when it was emitted. And so you can see these spectral lines, either in emission or absorption, in galaxies and various other things, and that's how you know what the photon's frequency or wavelength was when it was first emitted. And the redshift is just a comparison of that with what it looks like when you observe it. Andrew K. says, how can time be emergent if t is in the Schrödinger equation? Well, a couple ways. One is, of course, so anyway, I should back up and explain this for people who don't know. The Schrödinger equation is thought of as this complicated equation for quantum mechanics, but basically it's the time evolution equation in quantum mechanics. It says that if you have a quantum state, it evolves with respect to time in a certain way, depending on the energy, the Hamiltonian. So T for time appears right there in the Schrödinger equation. It is a fundamental part of the theory. It is not emergent in any sense. So there's two ways the time could nevertheless be emergent. One way is maybe the Schrödinger equation is not right. Okay, maybe you have something deeper than actual quantum mechanics. That's absolutely possible, but until you tell me what that actual thing is, it's hard for me to be specific about how that would happen. The other is that the Schrödinger equation is in some sense still right, but if the equation says the Hamiltonian H operating on the quantum state tells you the time derivative of the quantum state, then what if the Hamiltonian is just zero? What if the Hamiltonian annihilates the quantum state, as we say? Then h psi equals zero, rather than h psi equals d by dt psi. So in that case, it's still a special case of the Schrödinger equation, but time has disappeared from the equation. And indeed, this is not just hypothetical. In attempts to quantize general relativity, for a closed universe anyway, you get the Wheeler-DeWitt equation, which is precisely of the form h psi equals zero. And then you get what is called the problem of time in quantum gravity. Where did the time coordinate go? And the answer is it has to be emergent in some way. I'm not going to talk about ways it could be emergent, but it has to do, there's different options having to do with entanglement and things like that. But it does explain why time could be emergent even though it appears in the Schrödinger equation. Kyle Cabasares says, when writing your textbook Spacetime and Geometry, how did you decide what the end of chapter exercises would be? Were they a combination of questions you devised and variations of well-known problems from other relativity books? Yes, they are exactly that. I will confess that in the book, which I'm generally very proud of, I could have put more work into the end of chapter exercises and added more of them in particular. I was just trying to get, really focus on the actual content of the text. And there's other books out there, including most especially the famous problem book on relativity and gravitation, which I think, at least for a while, Princeton University Press had made publicly available for free. I'm not sure if that's still the case. But there's lots of relativity problems out there, so I didn't put too much effort into coming up with clever ones. But some of them I invented, some of them I got from other people, giving them to me. Some of them were just sort of classics that will appear in other books. Jose Gascon says, I am a computational chemist. I use software to solve the electronic structure of large molecules. Calculations typically scale as n cubed or higher. I presume n is the number of molecules. So for large systems, or the number of atoms, number of atoms. For large systems like proteins, such calculations become prohibitive. This is due to the non-separability of the Schrödinger equation. Do you think we will ever make a breakthrough, perhaps with alternative quantum theories, to solve the Schrödinger equation efficiently without the need for enormous superconducting capabilities? Well, I don't think that alternative quantum theories are going to be the way to do it. I don't know much about algorithms. So I'm very open to the possibility that there's some clever algorithm, some clever change of variables that for specific problems will make solving the Schrödinger equation easier. Look, if you have a free scalar field, which of course is a trivial problem, much easier than yours, But it's much easier if you take the Fourier transform. If you look at the field in momentum space as a sum of modes of fixed wavelength rather than in position space. So that's a simple solution, but maybe more clever ones work for molecules. That I don't know about. That's very possible. The other thing worth mentioning is, of course, this is the perfect place to look for applications of quantum computers. Quantum mechanics is hard. Quantum computers are slightly different than classical ones. We've been struggling to find examples where a quantum computer is worth building because it is clearly better than a classical computer. And one very, very plausible answer is when you're studying quantum systems, such as molecules, such as complicated molecules like proteins. So I would think about learning quantum computers and how they might help with these complicated problems. People are already on the case, of course, so you wouldn't be alone. Troy L. asks a priority question. This may be dumb and really basic, but what do we mean when we say the universe is 14.8 billion years old? By the way, I think you mean 13.8 billion years old, which we often round up to just say 14 billion years old. If time is relative, and how do we reach that number? What is the frame of reference? Does it mean simply that were we to run our clocks backward, we reach the singularity of the universe at minus 13.8 billion years Earth time? Is this a dumb question? So no, it's not a dumb question at all, because like you say, time is relative. More specifically, as we talked about with the twin paradox, two different clocks that move on different trajectories through the universe will end up reading different amounts of time elapsed. So how can it be that we have a single number for what the age of the universe is? And the answer is, in the real world, there is a reference frame that is preferred. The reference frame that is at rest with respect to the rest of the stuff in the universe. We don't live in empty space. We have stuff in the universe. We have the cosmic microwave background radiation. We have other stars and galaxies. There is more or less a rest frame for all that stuff. More specifically, there's a frame in which the cosmic microwave background seems to be at rest. So when we say the age of different things in the history of the universe, including the Big Bang itself, we mean as it would be measured in that reference frame. That's all we mean. Madeline Carr says, do you think that consciousness itself has any necessary function and or effect in the physical world, or is it simply a byproduct or epiphenomenon of independent physical processes? What proof is there to lean one way or the other? I think, actually, I'm going to group this question, because there's a question later on about compatibilism, and I forget where it is. It's later on in the file. I didn't group this in when I was organizing, so I'm going to do it in real time now. What is compatibilist free will, right? That was the question that is asked later on. And so compatibilist free will says that you talk about the human beings at the emergent higher level as agents that have the ability to make choices. It can be also true that there are lower level descriptions, whether in terms of neurons or elementary particles or whatever, but you are allowed to and can and should think about the higher level for its own sake, in addition to making sure that it is compatible with the lower levels. So both free will and consciousness, in my view, are manifestly real at that higher level. I don't know about you, Madeline, but I am conscious. I am aware of my surroundings. I have experiences and so forth. What I mean by that statement is that the best way of talking about myself as well as other beings is that they are conscious creatures. And what that means is that indeed there is causal power to that fact. It has different implications for the world if I say someone is conscious of a certain state of affairs or they're not conscious of a certain state of affairs, right? That leads me to make different predictions about how they will behave in the world. So consciousness, or free will for that matter, have as much causal impact in the world as tables and chairs do. They are not fundamental. They're not there in the standard model of particle physics, but once we coarse grain and look purely at the higher level, they play a very clearly important role. They're also not there if you look at the fundamental level, but that doesn't mean that they're not real. That's the poetic naturalist point of view that we were talking about earlier. So read the big picture for more. T. Van Reenen says, I I scrolled by accident. T. Sven Reenan says, listening to the podcast and reading your books, I'm always impressed by the way you concisely and clearly explain or express the most complex concepts and ideas. This also clearly shows when you summarize what a guest just said and usually come up with an easier or more accessible way to convey the same information. Could you perhaps explain what it is you do or don't do to achieve this? Well, thank you. That's a very nice compliment. I mean, I don't know what is going on there. I'm not following some magic formula or anything like that. I do, as I've often said, one of the nice things about Mindscape is not only am I the interviewer, but I'm also the booker. I choose who to ask to come on, so I'm genuinely interested in what they have to say. And, in some very real sense, I'm simple-minded about the things that I think I understand. I understand things when I can clearly see what is being said and how the different concepts fit together. So when I'm talking to somebody or when I'm just thinking about something and trying to explain it to somebody else, I am trying to simplify. I'm trying to boil down things to their essences, to strip away the parts that don't matter and to get to what does matter. Part of that actually, I'm just making this up. I haven't thought about it very deeply, but part of it might be related to the fact that I care about talking to a broader audience, right? That I care about doing podcasts and writing books, because there you can't get away with the various shortcuts and jargon words and things like that, the ruts that we fall into as professionals thinking about these things. You have to simplify as much as you possibly can. So you build up a sort of muscle that helps you take a complicated thing and simplify it down to the essence. Maybe that's true. I'm just sort of spitballing there. Ryan Vaughan says, as a physics layperson, it appears to me that there's a bifurcation of the field into theorists and experimentalists. Is that, in fact, the case, and if so, why? Can expertise in designing practical real-world experiments constrain one's ability to think freely about new theoretical concepts? I don't think it's the latter. I just think that the fields are very big now. I mean, there clearly is a difference between theorists and experimentalists, but their tasks are different. Coming up with theories, solving the equations, coming up with approximations and things like that is a different job than building an instrument, collecting the data, processing the data, understanding backgrounds and things like that. Back in the day, the number of theories and the complication of the experiments were such that one person or one group of people could do both. And now it's just harder because the theories are more involved and the experiments are more involved. It's like saying, can expertise in driving a race car constrain one's ability to be a Michelin-starred chef? No, those two things are completely possible, but they're both time-consuming, right? So very few people are Michelin-starred chefs and professional race car drivers. That's why not many people are high-level theoretical physicists and high-level experimental physicists. Nothing more difficult than that. The best ones in each camp talk to each other, but they're not the same person. Okay, we're going to group two questions together. Let's see if they make sense. Nikola Ivanov says, in your episode with David Deutsch, he stated that quantum field theory seems wrong to him because the field seemed discontinuous when two commuting, not causally linked, space-like separated field points suddenly become non-commuting, i.e. causally linked, when crossing the light-like borders of their respective light cones. This apparent jump in the quantum state of the fields bothers him. To the best of your knowledge, has anyone suggested a physical mechanism that could provide a possible explanation for this perceived discontinuity of the quantum fields? And then Nanu says, if we ever found the theory of quantum gravity, how do you think this achievement would impact our understanding of quantum field theory and the infinities that it encompasses? There seem to be conceptual discrepancies between infinite numbers of degrees of freedom in quantum field theory and finite number of degrees of freedom in gravity or black holes. It's hard enough to imagine that quantum field theory has significant gaps since experiments are delivered with high precision. So my question is, how would finding quantum gravity impact our understanding of quantum field theory? The reason why I'm grouping these two questions is because the answer to question one might be implicit in question two. In quantum field theory, by which we mean quantum field theory in flat spacetime, okay? Let's just take that we have spacetime as a fixed background, so we're not trying to do quantum gravity. So we're using now the phrase quantum field theory as something separate from quantum gravity. There are discontinuities. So what Nicola is referring to is if you poke a quantum field at one point in space-time, there are influences, ripples, that are strictly inside the light cone. That's just, you can't move faster than the speed of light, right? And that actually shows up even in the vacuum state. Even if you don't poke the quantum field, but just ask what are the correlations between what the quantum field is doing at two different points, you get different answers depending on whether they're causally connected or not. Does that bother you? So it bothers David Deutsch. It doesn't bother me. It doesn't bother most people who do quantum field theory. I mean, this is a fact. That is not one of the more bothersome facts, honestly, about quantum field theory. But also, it is probably not fundamentally true because gravity exists, okay? So because there is quantum gravity, the idea of space-time being a fixed background with well-defined light cones is probably just an approximation. And therefore, probably these things that seem infinite or sharp or discontinuous in the quantum field theory limit might be smoothed out and blurred and less troublesome when you also include quantum gravity. So to Nanu's question, yeah, I think that quantum gravity might have an important back reaction or important influence on how we think about quantum field theory. One very simple way that it does it is just to change how we conceptually worry about what happens at short distances and high energies. Namely, at the very least, we shouldn't be surprised to not understand what happens at short distances and high energies because gravity is going to be important at those levels. This paper that I recently wrote on non-overlapping degrees of freedom is one attempt, among others, to ask whether or not that influence of gravity might extend to longer distances and lower energies, the infrared regime, not just the ultraviolet regime, because that's where we can do experimental probes. We don't know what those, I mean, it's a very speculative paper. That's much harder to say what the impacts of quantum gravity could be, but it's worth looking because it might give us some crucial empirical clues. Matthew Wright says, in last month's Ask Me Anything, you said you'd reveal which episode of yours in the last year was recorded in person if we reminded you. What is it? So actually, I looked back and there were two of them. The one I was thinking of was Tim Maudlin, because Tim was actually visiting Baltimore at the time, and he came to my house, and we recorded the episode right here in the same place I'm recording it right now. But I'd forgotten there was another episode recently, which is Bill Egginton, who, of course, is a Hopkins professor. So we recorded that one in his office on the Hopkins campus. So I don't know whether the audio quality or the style of conversation was any different for those, but those were actually in person. Tim Converse says, I take it that we don't currently know of any experiments that would help us decide between, say, the many worlds interpretation and the Copenhagen interpretation, as they both predict the same experimental results. Do you believe that this will always be the case, or is there a possibility of finding differential experimental support for one or the other? Well, I think that the honest answer here is I don't think the Copenhagen interpretation is a well-defined theory. So I think that it is just incomplete. It is completely unfair to ask a complete and well-defined theory like many worlds to be experimentally compared with a vague and incomplete theory like Copenhagen. There are other complete theories that are not many worlds, like Bohmian mechanics or GRW theory, and there the situations are different. GRW is a situation where wave functions objectively collapse at random intervals, and yes, those random collapses have experimentally testable implications that we are trying to experimentally test. The interesting case is Bohmian mechanics versus many worlds. Now, someone like David Wallace would argue that Bohmian mechanics is actually not perfectly well defined because we don't know how to do it with quantum field theory yet, and quantum field theory is our best theory of nature. So until we can actually get a version of hidden variable Bohmian mechanics that plays nicely with quantum field theory, we're not sure what to say. But putting that aside, the people who are advocates of Bohmian mechanics would argue that where it is well-defined, it gives you the same experimental predictions as many worlds does. And there are arguments, and I understand what the arguments are for that. I'm not completely convinced by them. There might be loopholes. I don't think that people have tried nearly as hard as they could to find possible experimental discrepancies or differences between many worlds and Bohmian mechanics. So I encourage people to try to do that. I'm not going to spend much time doing it myself because I'm not that interested in Bohmian mechanics, but if I were interested in Bohmian mechanics, I would be bending over backwards to rather than show that it gives exactly the same experimental predictions as many worlds, to show that it gives something different. That would be super duper interesting. P. Walder says, universal teleology seems a popular explanation for accounting for meaning in life, e.g. Bostrom, Goff, Musser, Azarian, etc. What is your take on the notion that the universe, through some Darwinian-like process, is evolving and that consciousness is an outcome of such a process? I mean, there's a lot going on here. One is that, of course, the universe is evolving. That's what the universe does. Evolving just means changing with time. So yes, the universe is evolving. Is the universe undergoing natural selection, a la Darwin? I mean, Darwinian evolution, natural selection, is a very particular type of change over time. It requires that you have entities called organisms that have information about their structure that they can pass on to subsequent generations in some kind of hereditary fashion, but with modification, with either sexual mixing of genes or mutations or et cetera. Like all that setup is very specific. If you're not doing that, then you're not doing Darwin, okay? So things that are not biological, that are not Darwinian, can change over time. You know, the continents on the Earth move around over time. They evolve, but they're not being naturally selected in any sense. And the other thing to say is, of course, the whole point of Darwinian natural selection is that it is not teleological. There is no goal to natural selection. It adapts to whatever situation it finds itself in, but it doesn't see into the future and say, oh, I'm going to adapt my DNA or my genomes because something is going to happen in the future or because I want to achieve some goal. It is really moment to moment, simply selecting on what kind of genomes work for the situations you find yourself in. And I think it works very, very well. I think that's a perfectly good explanation. Read Dan Dennett's book, Darwin's Dangerous Idea, to really drive home the fact that it is explicitly non-teleological and it works really well. So I see zero reason in nature, whether it's in physics or biology or anywhere else, to invoke some sort of teleological aspect to the fundamental dynamics. Bart Shipper says, never would have asked you this, but on your latest appearance on Lex Friedman's podcast, you mentioned that you really want to be asked for relationship advice in your AMAs, so I am happy to oblige. By the way, I was partly joking about that, but I'm very welcome to be asked for relationship advice. I don't necessarily promise it will be good advice that I give. I'm not very good at giving advice in general. You know, that's why answering factual questions is easier for me than asking advice questions, but I sometimes try to give it my best shot. Anyway, Bart says, I'm a recently single 35-year-old father of two adorable little troublemakers. I work as a software engineer and have pretty typical nerdy hobbies like board games, etc. I'm a bit of an introvert, so going to random parties, etc. is not my idea of fun. These character traits were also part of the reason of the breakup of my relationship. I'm a bit worried I'll have a difficult time meeting women and sometimes fear I'll be alone for the rest of my life. Do you have any advice on how to approach this, given that society tends to look more positively towards the extrovert, outgoing type, and introverted people have, kind of by definition, a harder time meeting each other? I don't have a lot of advice for this kind of situation. I am also, myself kind of introverted in the sense that going to random parties, etc., and mingling with strangers is not my idea of a good time. I am someone who has the ability to act extrovertedly or to speak in public and things like that. But the typical introvert traits of those activities draining your energy and you need to go and be alone and recharge are very, very much my way of being. But my point of saying this is that being introverted doesn't mean that you can't mingle and socialize. Those are skills. Those are not automatically bequeathed to people just by virtue of being born. You can work at them and you can get better. And there are different ways to do it. I think I get one more relationship advice question later in the AMA, and I will echo something I'm going to say here, which is the single best way to meet people and eventually lead to some kind of romantic involvement is to just try to meet people without explicitly trying to make it lead to romantic involvement. Just try to meet people. Meet men and women, people who you like to talk to in different circumstances, people who you share interests with. You can do that on the internet. You can do it in person. You can do it by trying to do it. You can do it by letting it happen. It is true that it's much harder when you're 35 than when you're 23 and you're in college or just starting a job or whatever. It does become harder for all sorts of reasons. But Jennifer and I met when we were 40. And we met through, mutual interests online. We both had physics blogs, right? So you never know what the actual thing is going to be. But neither one of us were on the prowl looking for someone to marry or even to be romantically involved with. We just were interested in what each other were doing, and that's how it worked out. I tend to think that that's how it usually works out when it works out well. In other words, that you're not specifically looking for someone to get married to. You're looking for people to share interests with and to bond with in different ways. You do have to put yourself out there a little bit, right? That is, there's no easy way around that. Even if you would personally be most happy just sitting at home watching Netflix and eating pizza, you have to actually go out there and meet new people and talk to them. There are people, there are groups where people play board games and watch movies and talk about them and so forth. Think about ways to do that, So it's a mixture of taking a breath and working up the gumption to put yourself out there in some way and relaxing about the romance part of it. Just think about it as living your life. Maybe you don't meet a romantic partner, but you meet a lot of interesting people this way. There's certainly worse things that would happen than that. Zach McKinney says, in response to your solo episode comments about the societal impact of brain-computer interfaces and artificial intelligence, what aspects of natural human cognition do you believe are the most important to preserve and cultivate in a world increasingly dominated by artificial and augmented intelligence? To what extent should we individually and collectively invest in developing and maintaining the cognitive capabilities that can be easily replicated or surpassed by AI relative to learning to using such technologies as effectively as possible or honing human capacities that cannot yet be effectively automated? I think this is a good and important question, but a hard one to answer because the capabilities of AIs are still very much in flux, right? So they're getting better at certain things. It's hard but important to extrapolate those improvements to where they will eventually go. I think it's super clear that AIs are much better at mimicking human behavior now than most of us 5 or 10 years ago would have guessed they could be, but still falling very short of being human behavior. They still make all sorts of elementary mistakes. So are those elementary mistakes easily fixable or not? There's a whole bunch of people who think that those mistakes that AIs continue to make are fundamentally part of the package and they're not going to be easily fixable. Others are much more optimistic and think that's just a technology problem and we'll eventually get there. So I don't know what the capabilities are. Having said that, yes, I think it makes perfect sense when a new tool, forget about AI as a specific thing, whenever a new tool comes along that makes some existing human task much, much easier, we stop worrying about training people to do that task and let the tool do the task. I think doing your multiplication tables now is much less important than it would have been 200 years ago. We all have calculators on our phones, right? I'm sure you can think about manual labor tasks that are much less important now that we can automate them. And I think the same thing will be true with AI. You might personally take pleasure or pride in any sort of things that you can do, but if there is some AI that can do it just as well, then we can free ourselves to do other things by letting the AI do the things that we don't want to do. I'm entirely in favor of adapting to that in whatever way seems best suited to what those capabilities turn out to be. Niccolo Musmesci says, in some descriptions of special relativity, the speed of light limit is linked to causality. Surpassing light speed would allow effects to happen before their causes, which is impossible. But how is that a problem given that causality is a macroscopic emergent property rather than a basic physical law? I think that the thing to be honest about here is that physicists talking about relativity have borrowed the word causality but changed its meaning without telling you, okay? So before relativity came along, or even before Newtonian mechanics came along, if you were Aristotle and you were thinking about cause and effect relations, Aristotle had all sorts of different notions of causality, or really explanations is what he meant. But one form of causation is just the idea that there are events in the universe that we call causes, which are linked subsequently later in time to events that we call effects, right? There are causes and then there are effects. And that relationship is intrinsically time-directed. We always think that the cause comes before the effect in our everyday lives. And so when relativity comes along, we notice, maybe the thing to say is this. In a purely Newtonian world, before relativity came along, that would be the end of the story. Causes come first, effects come later. When relativity comes along, now we have a third category, right? From every event, there is a past and a future, but also space-like separated events that you could reach that are not in your past, but you could only reach them by going faster than the speed of light. And so physicists have taken that idea and adapted the idea that causes come before effects to say that causality limits effects from moving faster than the speed of light, right? Because if you are space-like separated, if 2 points are not related by either a past or future directed curve, then you can choose different coordinate systems in which those 2 points are in the past, 1 point is in the past or 1 point is in the future or at the same time. There's no fact of the matter about which the field, the event is in the future or in the past. It depends on your coordinate system, depends on your frame of reference. So therefore, physicists have just adapted the word, right? So when physicists in a quantum field theory book or in a general relativity book talk about causality, all they mean is that you can't travel faster than the speed of light. You can hopefully see how that descends from the Aristotelian/Newtonian view that causes precede effects, but it's a slightly different idea. That's okay. We often borrow the same terminology to refer to slightly different ideas. Okay, I'm going to group 2 questions together. Once again, slightly different questions, but hopefully you'll see the connection. Schreiberbike says, I find I agree with you on the vast majority of things, but I'm having trouble with the many worlds interpretation. The simplicity of the Schrödinger equation, creating a new universe every time an observation takes place is wonderful, but it asks a lot. My Bayesian priors put low credence on models that require the creation of universes just like ours, either more than once or some high number of times per second. I know a lot happens beyond the world I perceive directly, but in my mind, the frequent creation of universes like ours is too much. What am I missing? And then Mark Kumari says, I am thinking about electromagnetic fields. I turn on my TV and start watching the NBA and NHL playoffs. I then think about everyone around me doing the same, people speaking on the phone, someone listening to the Mindscape podcast, etc. It seems inconceivable that all that information is somehow just vibrations in a field and is really there in the space in front of me. So these 2 questions are not obviously related, but let me answer the second one, and I hope that you will see how it plays into the first one. When you say it just seems inconceivable, Mark, that all the information about the signals that we're receiving on our TVs, etc., are just somehow vibrations in the field. Why is that so inconceivable? What is so hard? I think all you're really saying is that your intuition is a little bit strained, that it seems like a lot of information contained in this very abstract, intangible field surrounding all of us. And indeed, there's a tremendous amount going on. If you think about the electromagnetic field at any one point, in fact, just the electric field, forget about the magnetic field, make your life easy. What do you mean? You mean that if you placed an electron at that point and it would jiggle around because it is being pushed by this fluctuating field called the electric field. And that electric field that is pushing around the electron is a combination of all sorts of waves, the light waves coming that you see with your eyes, but also the radio waves and microwaves that are sending signals around, infrared light from your remote control and what have you. And to decode, to extract all that information from the jiggles of the electron would require, some time domain data and then a bunch of Fourier transforms and quite elaborate mechanisms. But we can do it. We can build the technology that does it. And if you imagine that at every point in space, there's a field vibrating in a certain way, it shouldn't be that hard to imagine or to accept that there's an enormous amount of information contained. I mean, after all, there's an infinite number of points in space and an infinite number of ways an electron can jiggle. So there's a lot of capacity for the electromagnetic field to convey information. There's really nothing for me to say other than you should stretch your ability to accept very, very big numbers, like the amount of information contained in the fluctuating electromagnetic field. Hopefully you see how this connects to Schreiberbike's question about many worlds. All you're saying at the end of the day is that, wow, that's a lot of worlds. I don't like it. I don't see where they come from. It seems like a burden to create all those worlds, right? So many worlds. But that's just your intuition that only has experience with one world, right? Like, what in the world should your intuition have to say about this question? You can write down the equation. The equation is reliable. Your intuition has no right to be thought of as reliable in this particular circumstance. Remember, you didn't put in the worlds. All you did was take the Schrodinger equation at face value. Put it this way, as I often do. If you believe that an electron can be in a superposition of spin up and spin down, which quantum mechanics, taken as realist about the wave function, asks that you believe, then you should be able to believe that the universe can be in a superposition of many different things. It's just a matter of scale. Once you start believing in superpositions, you can't, it makes no sense. It is clearly your lack of imagination to be able to say, I believe that electrons can be in superpositions, but not that the universe can be in superpositions. The equations don't care. They're able to describe one just as well as the other. The relevant question becomes, does that superposition of the universe being in different states come to pass? Is it created by the time evolution of the universe? And the answer is yes. You can easily show that does happen all the time. So, suck it up. I don't know. I mean, of course, it's very, very different from anything that we experience in our everyday lives, but that's not a principled reason to doubt this theory. And if you really doubt it anyway, then come up with a better theory. That would be awesome if someone could come up with a better theory. No one would mind that. AJ says, do you subscribe to any Substacks or have any thoughts on Substack versus newspapers, magazines? I do not subscribe to Substacks myself. I do, read social media. Blue Sky is my current favorite, but I read different ones, and they link to Substacks quite often, so I'll read that. But my thoughts are kind of mixed. On the one hand, it's amazing to have the freedom both to choose to read a bunch of interesting people and for anyone to write, right? Whether it's Substack or anything else, the ability to go on the internet, start your own blog or newsletter or whatever is absolutely an improvement over the inability to do that we used to have. On the other hand, it does let you hide in a bubble if you want. It lets you read conspiracy theorists or disinformation experts, and if you want that to be your news diet, then you can be exposed to that if you want. So there is, in other words, a useful role for curation and editing and so forth. Like those things that might go away if we entirely move to individuals blabbing on their Substacks will be a loss, as opposed to newspapers and TV stations that actually have editors as well as reporters. Of course, another thing that is a loss is that the reporting aspect is supported by an institution, right? Newspapers think that they have a duty to report whatever is the relevant news for their beat that they're covering, and they put resources into it. They can pay reporters to go places, find information, and so forth. The Substack or blog model kind of rewards you for sitting back and, talking about stuff, not for climbing in your car and visiting someplace and collecting more information. People do it. People still do it anyway. But there becomes this greater emphasis on punditry and commentary compared to original news reporting. And as someone who's married to a journalist, I'm not making this up. The amount of resources and jobs given to people actually doing reporting has absolutely cratered in the last 20 years because of the internet. And this is absolutely independent of anything else. By itself, that's bad, okay? So there's good aspects and bad aspects. I don't know how it's all going to wash out. I hope that we still do have 50 years from now something called a reliable mainstream media. No media, mainstream or otherwise, is perfectly reliable, but we can work to make it better, and I think we should. Mario Boutte says, When you cover the topic of ADS-CFT, from time to time you bring the conversation back to Earth by saying, but this is not the real world, reminding everyone that we don't live in a universe of 2 + 1 dimensions with a negative cosmological constant. Would you apply the same argument as strongly when referring to the 6-dimensional space dimensions of string theory? No, absolutely not, because we might very well live in a world with the extra 6 additional space dimensions of string theory. They can just be compactified, and we don't see them. There's a huge difference between saying maybe something is there, we just don't know, like the extra dimensions of string theory, and saying this is a situation which we know is not true, like ADS-CFT. In ADS, the curvature of space is dominated by a negative vacuum energy. In our universe, we have, if anything, a positive vacuum energy, certainly not a negative one. So that's just wrong. That's not just speculative and unsure. That's just incorrect. It's still very worth doing ADS-CFT, even though it's not the real world, because we might learn something about qualities of quantum gravity, et cetera, that are then relevant to the real world. Ultimately, it's the real world we care about, and that real world may or may not be described by string theory with its extra dimensions. We just don't know. Spencer Hargis says, do you remember any ideas that struck you as incredibly exciting, but which seconds later you realized wouldn't work and never told a soul? How often has this occurred? Seconds later is an exaggeration, right? Usually if I'm very excited, the idea lasts for more than a few seconds. You know, my memory for these things is not that good. As anyone who listens to the AMAs over and over again will have gathered, you know, my memory for my own intellectual development is terrible. Like my memory for many things is terrible. My memory for the plots of books and movies is terrible. So I don't remember when it was that I got certain opinions. So usually if I have an idea and it doesn't pan out, I forget about it and move on to something else. A famous counterexample where I do remember is trying to modify gravity to get rid of dark matter and dark energy. I had this idea, and I've talked about this before, so I won't dwell on it, but I had this idea that both dark matter and dark energy come to be important in regimes of the universe where the curvature of space-time is small, either because you're far away from the center of a galaxy or because you're late in the history of the universe where the matter and energy has diluted away. So if you could modify the dynamics of Einstein's equation in a regime where the curvature was small, rather than in the regime where the curvature is large, where everyone expects it to be modified, then maybe you could help explain away both dark matter and dark energy. And I played around with that, and it didn't work. So I came up with a modification. It worked for making the universe accelerate and potentially explaining away the dark energy, did not work for explaining away the dark matter. So I got very sad. It was only when my collaborators came to me and we realized independently that this idea of just explaining the acceleration of the universe was intrinsically important, even if you couldn't also explain away the dark matter, that we wrote the paper, and that became a very highly cited paper. So that's always nice. Pete Faulkner says, I've been revisiting Roger Penrose's The Road to Reality after a hiatus of around 15 years and stumbled upon an intriguing comment regarding supersymmetry. In the book, Penrose suggests that one reason to question theories of supersymmetry is that the expected mass relationship between the Higgsino and the Higgs boson. He posits that, according to Suzy, the Higgsino should have a lower mass than the yet-to-be-discovered at that time Higgs boson, which prompts his question, if the Higgsino is lighter, why hasn't it been detected already? The actual quote is from section 13.2. It seems to be postulated that, of the two partners, the one that has the smaller spin by 1/2 h-bar is deemed to be the exceedingly more massive of the pair. Look, Roger Penrose is a genius mathematical physicist, and he was a former Mindscape guest, and he's contributed an enormous amount to our understanding of general relativity, as well as some pure mathy things, very deserving winner of the Nobel Prize. But he has weird ideas about a whole bunch of things, and this is an example. And this is an example, and there's other examples in that book that are sort of, you know, especially disappointing that his ideas are so weird. I mean, he has weird ideas about consciousness and quantum mechanics, but you can excuse that because quantum mechanics and consciousness are both things we don't understand that well. Supersymmetry we understand pretty well. All he had to do was ask somebody. When he says it seems to be postulated that of the two partners, the one that has the smaller spin is exceedingly more massive, that's just wrong. That is not what is postulated. You work out in the model of some particular supersymmetric theory what are the masses of the ordinary particles and their superpartners. And where he gets this impression from is the fact that in the standard model, we have spin 0 particle, the Higgs, spin 1/2 particles, all the fermions, electrons and quarks and so forth, and spin 1 particles, right, the gauge bosons. For both the spin 1/2 particles and the spin 1 particles, we can find superpartners of lower spin by 1/2. For the spin 0 particle, the superpartners will have to have higher spin because you already are at 0. So that's fine, that's okay. But the actual thing is that typically, and even this is not entirely true, but typically when you break supersymmetry, it's the superpartners that are going to become more massive, not the ones that have smaller spin. He just could have asked somebody. This is a completely made up fake worry. I don't know why he didn't. I mean, he's at Oxford. There's plenty of people who are experts on supersymmetry at Oxford. Sean Khanna says, do you find it challenging to devote enough time to your personal relationships and work simultaneously? How do you manage to make enough time for your partner, your professional goals, and hobbies/overall leisure? Well, it's a challenge. It's not specifically a challenge to balance personal life and work. I'm actually pretty good at that. I'm not, I like my work, so I work a lot, I work hard, but I have no trouble carving out time for personal fun things. I would like to be more flexible in my personal fun things. Like my schedule is a little bit cramped, so we have to, we'll have a date night a week and a half from now kind of thing. It's hard to be spontaneous. We have a very good friend of ours who is a neighbor here in Baltimore, Damon, who's always like texting us at 7 p.m. and saying like, come meet me for drinks. And we're like, we're doing something, or we're just too tired or whatever. I wish I could be more spontaneous than that. But within the different categories, there's always oversubscription. There's always too many things I want to do, and I'm not very good at balancing things. So it's catch as catch can. I'm not very systematic about these things. It's basically whichever thing is pressing upon me in the work side of things more desperately that I'm going to actually devote time to. I don't have anything more systematic to offer than that. Sorry about that. Eric Stromquist says, is decoherence really needed to isolate worlds under the Everett interpretation? I doubt Everett himself thought so, since Zay didn't discover decoherence until 1970. I should have, in retrospect, joined this question to the one earlier about dynamical fluctuations in empty space, because I think that they're related. So the answer is you're absolutely right that Everett did not rely on decoherence to isolate worlds in the Everett interpretation, but I do. Of course, we know about decoherence because Zay and others since 1970 have really explained it to us. And to me, it helps. I mean, one of the clear things about decoherence is not only that it tells you that worlds in the Everett interpretation will remain separate from each other, but it tells you which worlds remain separate from each other by solving the pointer basis problem, by explaining why the states that we see in the classical limit look like ones that have sort of semi-classical behavior, where objects have definite locations in space, etc. This is work that was done by Zay, but also Zurek and many others over the years. So to me, decoherence plays a huge role in the Everett interpretation, and indeed David Wallace's book will teach you the same thing. The reason why I relate it to the question of what happens in empty space is, in some sense, that doesn't happen in these decoherent histories in a static quantum field theory vacuum state. I mean, they do decohere from each other in some technical sense, but the pointer basis discussion is absent from that thing. And so I'm just talking out loud because this is stuff that I don't understand or anyone else does. So my guess is that the ultimate answer to the question of what happens in empty space is going to be that nothing happens in empty space because you don't have the kind of entropy producing, splitting, branching process complete with conventional decoherence a la Zay and Zurek, etc., that you're familiar with from pointer bases and their states in the real world. I would like to develop that suspicion into a more complete theory, but haven't done that yet. Ash Wright says, since writing the big picture, is there any topic from the book that you substantially updated your thinking on? I've grabbed a copy of my mom for Mother's Day and want to let her know that if there are any areas to take with an extra grain of salt. You're the best son, or Ash, I'm guessing your son or daughter, you're the best child, that your mother's going to very much appreciate the gift that you're giving her for Mother's Day, the big picture. There's nothing in the book that I would take back right now. Like any book, like anything I ever do, there are parts of the book that I would try to improve on. I guess the two things that I would want to improve on, but they're still consistent with what I've said, I would like to improve on the discussion of emergence, because I understand emergence better now than I did. Everything I said in the book I think is true, but I can say it better, more convincingly now. But it's still nothing that I would take back. And the other is in the section where I talk about meaningfulness and purpose in life. Again, I still agree with everything I say, but I was trying too hard to say things that I think are sort of indisputably true, and therefore maybe I didn't go out on a limb as much as I should have about, because I was trying to say like purpose and meaning are not out there in the world, you have to construct them for yourself. And I completely agree with that. But what do you construct for yourself? And I was pretty coy about that because I want to be a pluralist and let different people construct different things. But I think maybe the book would have been better had I been more explicitly suggesting, here's something that you can do to help build purpose and meaning in your life. I'm not exactly sure what that would have been, but if I were to produce a second edition, I would put more effort into doing that. Kyle Stevens says, my understanding was of your statement that the universe is a vector in Hilbert space is that you were suggesting that the universe is a purely mathematical structure. You also seem to reject Platonism and disagree with Max Tegmark's proposal of the mathematical multiverse. What then makes the existence of the mathematical structure that gives rise to our universe more real than any other mathematical structure? So I think I must be doing something wrong here because you're not the first person, Kyle, to say that they get that picture from me. And I'm not trying to say that the universe is a purely mathematical structure. I've never tried to say that. I don't think that. The universe is the universe. I think that the universe is a unique thing. The set of all reality is not something you can say it is something else. It's itself. There's only one version of it. There's only one copy of it. You can describe it. You can say what properties it has. And so when I say it's a vector in Hilbert space, what I mean is it follows the properties of a mathematical vector in Hilbert space. I can reconstruct or represent is the right word, features of the universe in terms of features of this mathematical object, a vector in Hilbert space. And to me, that's just obvious. And yet people don't seem to get that from what I'm saying. So clearly it's my job to be more explicit about this. In my mind, here is the analogy. Imagine that I draw a circle, and I'm very good at drawing circles. I'm not very good at drawing circles in the real world, but imagine that we're very good. I drew a circle on a piece of paper. And I say, here is a circle. And you say, oh, you're saying that is the Platonic abstract idea of the set of all points of a fixed radius from a single origin point in a two-dimensional space? And I say, no, that's not what I meant. Of course, this is just a particular representation of a circle. It is not the abstract mathematical idea. I thought you got the difference, so I didn't explicitly spell it out, okay? That's what I'm saying about the universe as a vector in Hilbert space. I can represent it as a vector in Hilbert space, but the universe is the universe. Not sure that means anything to say it is a mathematical structure. It's just the universe. Lucas Cost says, I've heard you say that science can't determine moral values, but do you think that we can in principle lean on scientific knowledge to help us develop well-justified moral beliefs? If we accept that the goal is not absolute moral certainty, but instead to develop well-justified beliefs about moral questions, then can science have something meaningful to say on morality? Of course, science can have something meaningful to say about morality in the sense that if we have moral goals, if we have a moral theory that says this action would be more moral than that action, it had better be compatible with the real world, right? So, I mean, let's imagine that you had some moral theory that prioritized happiness. We could absolutely do science to show that this makes people happy, that doesn't make people happy, right? What science can't do is help us come up with those goals in the first place. The way to think about it, the poetic naturalist way to think about it is there is a world. There is the physical world of which we are a part. Science describes that. Science helps us explain the physical world, both at fundamental levels and emergent levels. And the scientific explanation is sort of rigid. There's a correct one, and there are many, many incorrect ones. Morality is a set of judgments. It's saying that this hypothetical action would be labeled as bad. That hypothetical action would be labeled as good. There's no way by just measuring what the world is to figure out what those labels should be. But of course, we can use scientific knowledge to actually achieve what those moral goals are. I'm going to group two questions together because they're basically the same question. Ken Wolf says, in New Scientist, I read an article describing a new variation on the many worlds interpretation of quantum mechanics that they simply referred to as the many more worlds interpretation. There were a couple of quotes from you that suggested you were at least familiar with it. The part of their description that struck me was a more or less arbitrary division of the world into subsystems, some of which could lead to subsystems that behave in a classical way. I find this puzzling since you always seem to describe the Everett interpretation as positing a division of universe that behaves in an approximately classical way into two complete universes that diverge in one way and are from that point invisible to each other. I feel that this is some more fundamental difference in this many more worlds interpretation that I am missing. Can you shed any light on this? And Girolamo Castaldo says, what are your thoughts on the recent many more worlds hypothesis? So I've heard questions about this before, and I got confused by this. I was like, I was quoted in a New Scientist article. I don't know what this is about. So I finally figured out what it's about. I haven't read the article. I haven't seen the article, even though I was quoted in it, and I did talk to the reporter about it. But it's about a paper that was written by Andy Albrecht and some of his collaborations on what the same exact topic that Ashmeet Singh and I wrote a paper on earlier, and we called quantum mereology. It's not a new interpretation of quantum mechanics. It's not even a modification of the many worlds interpretation of quantum mechanics. It's just a question within many worlds, which is how do you take the wave function of the universe or the quantum state of the universe and divide it up into subsystems? That's it. That's all that it's about. There's nothing more in the interpretation than that. It's just many worlds. It's a question about many worlds. The difference is, in the paper that I wrote with Ashmeet, we proposed two criteria for dividing the world up into subsystems. What we're looking for is subsystems that will behave more or less classically. So you have a system that is going to behave more or less classically, and then you have the environment, which is everything else. So I am part of the system that you might have here in this room. All the photons that are hitting me right now are part of the environment, and I trace out all those photons to get classical-looking behavior for myself. But something that is not clear if you're not if you don't know quantum mechanics at the mathematical level is that that division of what's going on in my room right now into like me, table, photons, etc. is something that we choose. It is not fixed by nature. We could divide the world up in many, many different ways. Most of those ways would make no sense. Most of those ways would not give you a well-defined fact of the matter about what each subsystem is doing. Indeed, this was a point that Dan Dennett made in his paper about real patterns. That's why David Wallace relied on that paper when he wrote his book about the emergent multiverse, about the many worlds interpretation. Anyway, Ashmeet and I suggested that when you have a classical subsystem and an environment, what that means is two things. One is that the system, if it is localized, so if like you have the Earth and it has there's a wave function for the Earth, but the Earth remains pretty localized around its center of mass coordinate, right? So if it's localized, it doesn't spread out its wave function. And then the other one is that it remains more or less unentangled with the environment. So if you have Schrödinger's cat, and so you have a cat that is in a superposition of two macroscopically distinguishable states, that instantly becomes entangled with the environment because the environment interacts with those two states differently. Whereas if the cat is in just a single classical-looking, macroscopically coherent-looking state, photons are absorbed or bounce off of it, but they don't become entangled because entanglement means you're interacting differently with different parts of the wave function. So you have those two criteria, and we claimed that those two criteria, localized states remain localized and unentangled states remain unentangled, are enough to uniquely pick out what is the right way to make a classical subsystem. What this new paper by Albrecht and collaborators says is that there is not a unique way to divide the world into subsystems, but they also don't have two criteria. They only have the one. They only have the fact that the initially unentangled states remain unentangled. I have not read the paper super duper carefully. I think that's the difference. They have less stringent requirements on what they mean by a way to dividing the world up into subsystems, and therefore they don't get uniqueness. That makes perfect sense. And then we can argue about whether or not you should have those two criteria or not. And that's a perfectly legit scientific question. But to help Ken understand his question, what is going on here is taking a single world and dividing it up into subsystems. It's not literally about how many worlds there are, unless it's not that there are many more worlds at once. Let's put it that way. It's that if you don't believe there is a unique way of dividing the wave function up into subsystems, then you could have a single wave function with different ways of dividing it up into subsystems, and therefore different ways of dividing it up into worlds, right? So it's not that there are more worlds at any one time in any one division. It's not that you're slicing the world more finely. It's that there are different ways of slicing the wave function of the universe up into worlds. Like I said, I don't really think that's true, but that's what is supposed to be going on here. It's not in any sense a different interpretation of quantum mechanics. It's still saying there's one wave function that obeys the Schrödinger equation. And so, I think that I say positive things about it because I want people to be asking this question. I think this is a centrally important question that Ashmead and I wrote about, and some other people wrote about who we cited, but not very many people have written about this question. And so I'm happy to have other people talking about it, even if they reach different conclusions than we are. That's how science works. We're going to all write papers and talk about it and discuss it, and hopefully the right answer will come out in the process. Rob Butler says, I found the episode with Matt Strassler really interesting. One thing that was slightly glossed over at the very end of the episode was regarding the mass of protons and neutrons. He said that the Higgs field is responsible for the mass of elementary particles, but protons and neutrons get their mass from somewhere else, but didn't elaborate. Aren't protons and neutrons made from quarks? Well, no, not exactly. They're not really made of quarks. This is something that you could read Matt's book to find more details about. You can read my upcoming book to get more details about, or you can read my previous book, Particle at the End of the Universe, to get more details about. There's a short version and a longer version. I'll give the short version and then hint at the longer version. The short version is that in the protons and neutrons, there are quarks, but there are also gluons holding the quarks together. Unlike an atom, where you have electrons and nucleons held together by photons, in the protons and neutrons, those gluons matter. The strong nuclear force is a huge contributor to the ultimate mass of the protons and neutrons. That's just different from atoms. So therefore, it turns out that the actual mass of a proton and neutron is mostly gluons in some very real sense. It's not the quarks If you added up the masses of the up and down quarks and protons and neutrons, the number you would get is much smaller than the total mass of a proton or neutron. The slightly longer answer would be that really inside a proton or a neutron, inside a nucleon in other words, is a regime where thinking about quantum fields as particles is not a good approximation anymore. So in my book, I discuss in some detail about when you should think of quantum fields as particles and when you shouldn't. And what's really going on in the protons and neutrons are complicated interacting combinations of the quantum fields representing the up quark, the down quark, and the gluons. And at the end of the day, you're going to get a mass, but that mass is not going to be related in any simple way to the masses of the underlying particles that you would imagine thinking about if you just had one field at a time. Raj says, is it possible that the learning of or about the universe that we humans do is actually just fulfilling some kind of evolutionary need for building a framework of reality, or are we actually transcending biological limitations and reaching far beyond with our unique brains and invented math? I don't know what that second one means. Certainly we're fulfilling some kind of evolutionary need for building a framework of reality. That's part of our survival here on Earth. I don't know what it means to be transcending our biological limitations. So I don't think it's just anything. I don't see what the word just is doing in there. We are physical creatures. We are obeying the laws of physics, and we are also obeying the biological reality of natural selection. And we can explain what happens inside our bodies because of that. And through biological time, we can see how greater and greater capacities to understand the universe have been developed. And they serve a very obvious biological purpose. The more we understand the world, the better off we can survive in it and live in it. And I think that that sort of fits together very nicely. Adriana Sosserman says, does faith have a role in science? Not necessarily in the religious context, but the concept of believing in something without needing proof. Almost entirely no is the short answer. It depends on what you mean by the word faith here. I know that you tried to define it a little bit, but there's still some fuzziness there. Scientists don't accept things on faith. We hypothesize, and then we test our hypotheses. But we do have certain preconditions for imagining that science works, right? Like if we are living in a simulation or we are brains in a vat being taunted by an evil demon, then the conclusions that science reaches will not actually completely correctly represent the true external reality, okay? So I think that science has some preconceptions, some preconditions, some assumptions under which it works. But it's not faith because any of those assumptions could be undermined. If we live in a simulation or our brains in vats, it could be revealed that that is true, or we could even discover it scientifically. We do need some very, very weak assumptions about the intelligibility of the universe. The idea that the universe makes sense is just an assumption that science has to make. But again, it's not faith because we would be willing to change our minds if good reason came along to do so. Robert Grenace says, I have been a Patreon subscriber since pretty much the beginning. I've learned so much. Burdened with religious education, I grew up in a constant state of existential terror. How can we be here? How could we not be here? The more I have learned, the less afraid I became. I've heard several times on the podcast people writing to express the same fears and looking for solace. At a planetarium years ago, I was overwhelmed by the scale of the universe and gripping the armrests in panic. Near the end, the voice talked about a colony of microbes that lived under the hood of a mushroom. They lived only one Earth day. The elders would tell the children that historians say at some point the light in the sky would go out, nightfall, and they would perish. The children were inconsolable until they were told that the stories also assured them that the light will someday return. I felt it, by the way, that sounds like an Isaac Asimov story called Nightfall. I felt at peace. Without a God and afterlife to lean on, the concept of the heat death of the universe is pretty bleak. It doesn't seem right that the cycle of life should simply peter out. In your solo episode, you talked about the notion of little big bangs self-generating out the universe at maximum entropy. I got a similar good feeling from that. Perhaps if another listener comes to you for consolation from these fears, you could tell them about this possibility. It could make a difference. Yeah, it could make a difference, but I wouldn't want to rely on that. The idea that the universe regenerates sometime in the future, that there are future big bangs and multiple universes, or similar related ideas that the universe is bouncing and cyclic and lasts forever in that way, these are, as we were just talking about, scientific hypotheses. They may or may not be true. I would not want my feelings about the worthiness of the life I am living to rely on the possible truth or falsity of those scientific conjectures. We don't know whether they're true or not. They might be false. And I think that the meaningfulness of life is actually contained in the actual span of the life we live. These theories that we're talking about are talking about things that will happen billions and billions and billions of trillions of quadrillions of Google years in the future. They have no real connection to my life here on Earth. So I don't, even though maybe it is true that explaining those scenarios could help some people, deal with and accept the reality of the natural world, part of me wants to say they shouldn't. I think that's the sort of a false consciousness. That's not really the reason why you should find meaningfulness in the world. It should be about the life you're living here, finite as it is. That's why in the big picture, I have a chapter that emphasizes that the average human lifespan is about 3 billion heartbeats. I don't want people to look away from the finitude of our lives. I want to face up to it and accept it and use that to construct something truly meaningful during the 3 billion heartbeats that we have here. Jeff B. says, what are the statements about which you have a credence of absolutely 0% or 100%? Well, very few, effectively. I want to say none, but I think that it depends exactly on what you mean, okay? You did put the word absolutely in there, which makes a difference and makes me say none, because if you have credence of 0% or 100% in anything, then you're making it impossible to change your mind, right? You're not allowed to change your mind as a good Bayesian. No new evidence could possibly change your mind about anything. So I don't want to have 0% or 100% credence about anything. But in the real world, my credences about some things are so enormously small or enormously large that for all intents and purposes, I'm not worried about changing my mind about it. I don't dwell on the possibility. So, and I don't have a list of those statements, but they're pretty obvious ones, I think. Qubit says, I understand that a dice roll is a classical phenomenon, and we therefore do not expect an equal branching into 6 worlds. The apparent randomness is just based on our incomplete information about the initial state and the chaotic time evolution, which amplifies changes in this state. However, one could argue that even the quantum mechanical uncertainty in the initial state will be amplified by this mechanism, thereby leading indeed to 6 branches with roughly equal weight. Is there a simple counter-argument? This is something I don't know a lot about, but I will mention that Andy Albrecht, who we just mentioned in the many more worlds interpretation context, has written about this. Andy wants to claim that in the real world, when we do flip coins or roll dice or shuffle a deck of cards or do other things that we think about are truly random looking, like if you shuffle a deck of cards badly, or if you flip a coin in such a way that you are a practiced magician who can always get the same outcome of the coin flip, then okay, that's different. But if you do things in ways that most people would recognize as effectively random, Andy wants to argue that it is always quantum mechanics that is at the basis of that randomness. In other words, that there truly are worlds of roughly equal magnitude where all the outcomes come to be. And the argument is based on very, very small quantum uncertainties growing through essentially chaotic dynamics, just from the signals passing through the neurons in your brain to your fingers that are rolling the die or flipping the coin or whatever. I have done zero work to think about, work on, or understand this claim, so I can't tell you whether it is true or not. But I think it's a perfectly open possibility that is worth looking into if you care about this kind of thing. That's all I will say. Mark Foskey says, if you don't accept ethical realism, what stance do you take towards others who violate ethical principles that you personally hold? When you get indignant when one person hurts another, do you regard that as an irrational emotional response and try instead just to be sad rather than angry because no objective moral code is being violated? No, I do not do that. I get angry, and I think that it's perfectly rational for me to get angry because that's in the nature of having a moral code, whether that moral code is objective or not. The word objective is playing no role in that sentence. If I have a moral code, then I believe that certain things are right and certain things are wrong. Not objectively. I didn't say objective. I said I believe, right? It is a systematization and a turning into a rational codification of my moral intuitions. And then I believe that other people should obey those moral intuitions. That's what I think, okay? Now, other people will have incompatible moral intuitions, and the point of being an anti-realist is that the two of us have irreconcilable differences. We can talk to each other, we can try to persuade each other, and often that works in the real world. But there is not either an empirical experiment or an airtight logical argument that we can give that forces one person to change their mind, okay? But nevertheless, that doesn't stop us from having our opinions, our feelings about these things. So people who are moral realists, think that unless something is objective, it doesn't exist. But that's just not true. That's not true logically, metaphysically, or et cetera. Again, I talk about this in great length in the big picture. You can read about the idea of moral constructivism, which is different than moral relativism in exactly this way. Paul Hess says, matter can change state at different temperatures and pressures. In the dense early universe, could dark matter have been in a different state and maybe interacted in a more significant way that left a footprint? Well, I'm not sure what footprint you're thinking about, but yes, dark matter could absolutely be in a different state. I mean, it almost certainly was in a different state. Dark matter Well, I shouldn't say almost certainly because we don't know enough about what the right theory of dark matter was. But let's say that you have the conventional weakly interacting massive particle, dark matter. In the very early universe, that dark matter was interacting with each other, moving relativistically, etc. At some point, it freezes out, as we say. It stops interacting, and it becomes non-relativistic, and usually it becomes non-relativistic first, freezes out later if it's a cold dark matter candidate. But the point is, yes, dark matter undergoes changes of phase as time goes on. What we seem to be told by the data is that there's kind of a robust vanilla feature of the dark matter, where at the end of the day, it is a cold, non-interacting particle that is distributed in a certain way called, adiabatic Gaussian initial conditions. And there's not much more to say beyond that. If dark matter had interesting interactions either early on or later on, we might be able to see that, but we haven't seen any evidence for it as yet. Voltaire O asks a priority question. I have delved deep into the big questions through science and philosophy and have still not found an answer to why something, not nothing. It is so weird that I, we, or anything exists. All the scientific and philosophical answers still leave me unsatisfied. Boltzmann brains, etc. How do you feel about existence? I did write a paper about this. You can Google why is there something rather than nothing, Sean Carroll, and you can read my paper about it. The short version is, I don't think there's an answer to why there is something rather than nothing. I think you have to think carefully about what you are asking for when you ask a why question. There's no logical reason why every why question has to have an answer. In other words, why there has to be a reason why every fact of the universe is the way it is. The argument for that is just that I could easily imagine a different kind of universe in which different things happened, right? And so there are going to be some features of the universe that are contingent, that are just brute facts. And I think that the existence of the universe itself is exactly that kind of thing. It is true, but it's not something where we're going to find an answer that says, here's why it's true. And you just have to learn to live with that, just like the finitude of the universe. There are things, or the existence of many, many worlds or whatever, right? The universe isn't there to make us happy, and the universe certainly isn't there to conform to our intuitions developed over biological time or the decades we have here on Earth. You got to learn to stretch your intuitions and to live with what the universe actually is telling you. Anonymous asks a priority question. In a YouTube video entitled The Nature of Reality, Alan Wallace suggests that consciousness exists beyond mind and is somewhat unexplainable. You object. So this is a dialogue I had with Alan Wallace that he's referring to. You object, saying no one can explain the mechanism by which this unexplainable phenomena of consciousness interacts with the human mind. Please comment on the following attempt to bridge these two views. And the Anonymous writes a lot of paragraphs. Even if it's a priority question, I got to mention, you still have to obey the rules of the AMA. One of the rules is keep it short. So I'm going to try to edit it down to a short version. In another lecture, you present the core theory. One of the terms included addresses all known frequencies of electromagnetic forces. There are several research papers which report success in measuring chi energy and placing it in the infrared range of the electromagnetic spectrum. My hypothesis is that what Wallace refers to as an unexplainable consciousness is in fact a measurable electromagnetic force. I mean, maybe. I'm highly doubtful for several reasons. Number one, I guess, for one basic reason, I'm perfectly happy with imagining that there are electromagnetic forces that influence us because that is obviously manifestly true. No one argues with that. There certainly are electromagnetic forces. They certainly do influence us. I think that when people talk about a consciousness that exists beyond mind, or when people talk about chi energy, etc., they have something in mind that is different than electromagnetic forces. They do not have equations of motion for their consciousness or their chi field or whatever. They would feel cheapened if you said, oh yes, here's my equation for how this field works. Whereas I have equations for the evolution of the electromagnetic forces. It's right there in the core theory. It's purely physics. It's purely mechanistic. There's nothing spooky about it. We actually understand the electromagnetic field super duper well. So I'm perfectly happy with attaching different labels to electromagnetic forces. I suspect that these other people who want consciousness to be other than physical would not be happy with that identification. Callan says, I recently watched your appearance on Lex Friedman's podcasts. Lex Friedman's podcast. Sorry, it's getting late, folks. In it, you said you wished people asked you more questions regarding relationships, although I think you were saying it somewhat jokingly. I thought I'd ask you. I was saying it jokingly, but with a serious joking intent. Like, I don't care whether people don't. I'm not really insulted. That was the joke. But I'm very happy if people want to do it, and I may or may not pick your questions. That's what I meant. Anyway, Callan continues. I've been with my girlfriend for almost 6 years now, and sometimes it can be a struggle to keep things fresh. We have a 3-year-old daughter, so that can definitely make it a challenge to make time, especially with work and studies. How do you and your lovely wife, Jennifer, keep things fresh and keep the spark alive, so to speak? I know some people think that if you love someone, that you're in a relationship, it's like some Disney story with no rough patches, but I don't think it works that way. So what's your advice generally on having a good relationship with your significant other? Yeah, so this is another case, even though I requested or solicited romantic advice questions, the real answer is always that everybody is different. And you have to find your road. You have to figure out the way to make it work for you. So therefore, I can't tell you what to do. I can offer a few hints as to how it works for us. One is that we're just super lucky, Jennifer and I, to be as compatible as we are, and we don't have many rough patches to speak of, so there's not a lot of work to be done in getting over them. But that's not very helpful advice. I can think of 2 slightly more tangible pieces of advice. First, in terms of keeping your relationship fresh and your relationship interesting, I think the primary thing is to keep your life interesting. If you 2 individuals lead interesting lives, then it will naturally happen that your relationship becomes interesting. I mean, you want to spend time together, but you also want to lead separate lives. You want to have separate interests that you can then talk about when you come together, right? You don't want to watch all the same movies and TV shows or read all the same books or meet all the same people. You want to be a little bit independent so that you can come and share something that the other one has not known about. Right? You want to do interesting things. Again, it has nothing to do with the fact that you're in a relationship. You just want to live a life that includes all sorts of different things happening so that you look forward to new things happening with anticipation. And if you're in a successful relationship, you will anticipate sharing that, either the recollection of it afterward or the experience of it in the moment with your partner in a very natural way. So keeping your life interesting is the simplest route to keeping your relationship fresh. The other one is, in terms of rough patches and so forth, I'm not exactly sure how to put this exactly right because it seems kind of obvious to me, but maybe it's not what actual people always do, which is you have to orient yourself, either naturally or by training yourself, to get pleasure out of making the other person happy, right? It's never going to be the case that the things that make you happy are exactly the same as the thing that makes your partner happy. You're different human beings. That's perfectly natural. Some of them you will want to be able to do, and your partner will just let you do them, okay? Others, you're going to want to have to share that experience, as we said. But in terms of what brings you happiness, some part of that has to be doing nice things or otherwise making your partner happy. You can't be completely selfish, in other words, to put it more basically. Your relationship success can't be about, well, they're not paying enough attention to me, they're not making me happy enough, unless you're doing everything to make them happy. If you actually take pleasure, if you actually find fulfillment in making your partner happy, then the relationship's going to be good. Doing nice things for them, listening to them, understanding what it is that they think would actually make them happy rather than telling them what should make them happy, all those sorts of things. I'm not sure if it's very useful advice because to me, it's just sort of being a good person is the way to do it. So keep your relationship fresh by having an interesting life. Keep your relationship happy by being a good person. That's as blasé as my advice gets. This is why I'm not a good relationship columnist. Sorry. Connor Kostick says, it's easy to arrive at the concept of infinity, but is there anything we've observed in nature that is definitely infinite? Infinitely small would count, e.g. a singularity. No, absolutely not. The reason why infinity comes up in physics is because we extrapolate, right? Think about the integers. No one has ever seen all the integers. 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, etc. The reason why we say the set of integers is infinite is because we write down an integer, or some finite number of them, plus a rule for generating more, and we say, and the rule never stops, right? So we have a generative procedure for constructing this infinity. But that doesn't mean we've seen it or experienced it. And that's even just the integers, much less the continuum of real numbers, etc. So in physics, we find that our mathematical models that best fit the world often take advantage of this idea of a smooth continuum of numbers or an infinite number of integers or whatever. But you don't see it because you're extending, your theory covers a whole bunch of cases that you haven't personally experienced. It is absolutely possible that there is no infinity in nature. I recently wrote a paper suggesting exactly that. But it doesn't quite work, doesn't quite exactly work. It almost works, but there's slight problems there. On the other hand, maybe it does. I think that it's more likely than not that infinity does exist in nature. But we human beings are finite. So I don't even know what it would mean to literally observe an infinity. That is to observe anything where we can be absolutely definitive about saying that this quantity that we're observing is infinite rather than just really big. I'm not sure if human beings have the capacity to draw that distinction in a reliable way. Physics Kitten says, as you pointed out in your Crisis in Physics podcast, the cosmological constant is 120 orders of magnitude lower than we think it should be by computing the zero-point energy of empty space. Doesn't this cause you to increase your credence that we are living in a simulation? I mean, maybe, but an infinitesimal amount. It does not have a very big effect. Look, there's plenty of puzzles in physics. At any one moment in the history of physics, there were plenty of puzzles we didn't know the answer to. If at every moment you said, well, I guess that's probably evidence we live in a simulation, you would have been wrong almost all the time, right? Right now, there are features of the universe that we don't have good explanations for, like the value of the vacuum energy. To instantly leap saying, therefore, it's evidence that we live in a simulation, I think that's just not a very good way to make progress. I can think of plenty of plausible, well, at least conceivable, physical mechanisms that would explain the small cosmological constant without relying on living in a simulation. Furthermore, I don't know why a simulator would want to make the cosmological constant that small. So in terms of the likelihood functions, maybe there's a small boost to the likelihood that we live in a simulation coming from the cosmological constant being small, but it's not a very appreciable one. It doesn't change my credences that strongly. Lackmere says, as a software developer, I'd be fascinated to learn about the software that applies to your day-to-day physics work. For example, what programs do you find helpful? What are you trying to do when you use them? And how do they help you do that? You know, as I've said, I am mostly a pencil and paper theorist. So the two most important pieces of software I have, well, all right, what are the most important pieces of software I have? And I'm going to put aside the podcast, okay, because you said day-to-day physics work. Gmail, Chrome, LaTeX. Actually, I need to use Microsoft Word a lot because I don't just write physics papers, right? So for anything in the real world, you still need to use Microsoft Word, although I use Scrivener if I'm writing a book-length project. But LaTeX is certainly my preferred way of writing anything with equations in it. The biggest ideas in the universe had to be written in Microsoft Word because that's the only thing that the publishers would accept. And it has been a terrible, terrible experience to try to get those equations right in Microsoft Word, I have to tell you. And I draw things in Affinity Designer. That's a illustration program. So I draw figures and things like that. And I use Mathematica to do simple numerical calculations. Plus, occasionally I'm forced to do some Python coding, very simple Python coding. And I do use either ChatGPT or GitHub Copilot to help have AI propose little ways of writing subroutines. It only works if you're writing something that other people have written already, right? So it's basically an elaborate way of copying other people's code, as far as I can tell. But again, mostly my actual work is done at the Blackboard or at my iPad. Notability is super important for me. On my iPad, I have Notability, which is a way of both writing with the Apple Pencil, writing documents, marking up PDFs, signing documents, things like that. So I think at the end of the day, the answer is my software use is highly non-sophisticated and nothing that should impress anybody else. By the way, I will mention that I'm an old school programmer. When I grew up, it was Fortran and BASIC. that I was programming in. I mean, I took classes and learned to program in assembly language and a little bit of C++, I think. I've forgotten all of that by now. Probably I could remember a little bit of Fortran and BASIC, but obviously it's been a very, very long time since I've done that. I could have, again, if I had been, I've always been very bad at thinking carefully about what to do in the future, given what I was doing in the present. Like, I did a lot of programming as an undergraduate and then very little as a graduate student, but some, and then almost none ever since then. But I easily could have been on the forefront of programming because my undergraduate days were in the early 80s when it was not overwhelmed with people doing it. But I'm perfectly happy having chosen to do more pencil and paper kinds of things. Nomad666 says, can you please explain compatibilist free will and what does free will really mean? Is it having ultimate control over our internal and external actions? And do we or can we even have control over our internal and external actions all the time? So this is what I mentioned earlier when we were talking about consciousness as an emergent phenomenon. I think that's what compatibilist free will is. I've said it many, many times. I will say it again. Compatibilist free will, to me, simply means that the best description of human beings at the level of human beings includes the idea that human beings make choices through deliberation over different possibilities. That's what it means. I keep saying that. People don't seem to get it. The people who don't believe in compatibilist free will, I've never met one who could tell me what compatibilist free will means. They have some weird version of it that exists in their brains. I'm sure they're out there. I'm sure there are people. I'm just saying that I've never had that experience myself. I don't want to go into that again, but the reason why I wanted to answer this question is because there are different reasons why people struggle with this concept. And I think that it does actually require thinking philosophically carefully about things. So in Nomad's question, he or she says, is it having ultimate control over our internal and external actions? And do we or can we even have control over our internal and external actions all the time? Okay, so what do you mean by we? That's the philosophy question here, right? By using that word, you're presuming that there is some concept that maps onto the word you or I or we or whatever, right? That there is some person, that there is some in nature, some object that is usefully described as being this particular person. Okay, so you're going to have to be careful if you want to ask these questions, if you want to relate that person to their internal and external actions. I'm not even sure what internal actions means. Like, it doesn't mean I can control my heartbeat or anything like that. So I'm not sure what that means. My external actions, yes, at the level of talking about the world in terms of human beings and tables and chairs, I say, look, this person made this action because they chose to do it. And I don't get people who somehow pretend not to understand what that sentence means. Sam Harris, when I was on his podcast, literally said, like, have you ever made a choice? Yeah, I made all sorts of choices. Like, what does that mean? You have to be redefining what it means to be a person and making choices. You have to be forgetting that is a way of talking about human beings and pretending that what I'm really saying is, have you sort of superseded the laws of physics and the motion of the atoms in your body? No, I have not superseded the laws of physics in any way, but I'm not talking about atoms in my body. I'm talking about me as a person. Me as a person makes choices. That's the way the compatibilists talk. I shouldn't say that. That's the way everyone talks. Compatibilists just admit it and says it's okay to talk that way. Mark says, did you meet and know Cormac McCarthy at the Santa Fe Institute? As exhilarating as high-level cross-pollination can be, is there a real potential downside in being distracted away from your particular discipline, a drift towards cocktail party intellectualism? I didn't actually ever meet Cormac McCarthy at SFI. We didn't happen to overlap just by chance. Plenty of people who I knew who visited there did interact with him quite a bit. I'm all in favor of interdisciplinary cross-pollination. I think it's called having an interesting intellectual life. I'm not sure why we would be worried that we're being distracted away from more serious things. The question, there's always a question of what have you produced? If your job is being an intellectual, being a creator, being an academic, being a scholar, however you want to put it, it's nice to imagine sitting in your reading room in your smoking jacket, reading some books and contemplating great ideas, but that's fun. That's not what you're paid to do. What you're paid to do is produce, okay? So I'm all in favor of judging people on the basis of what they produce. What papers have you written? What books have you written? What contributions have you made, etc. That's fine. But how they get there is up to them, I think. I think that some ways of making huge intellectual progress involve being very focused and narrow-minded, just thinking about this particular problem to the exclusion of all other problems, hitting away at that problem for years and years and years. I mean, arguably, I don't know the details, but arguably someone like Andrew Wiles solving Fermat's last theorem, proving Fermat's last theorem, is just a matter of taking one problem and beating away at it for a very, very long time. But there are other people who get great insights from absolutely interdisciplinary cross-pollination. Jeffrey West, former Mindscape guest, taking ideas from biology and physics and network theory and putting them together to come up with a new explanation for allometric scaling laws. There you go. So I don't care how you get there. I care about where you go. And many different people will get there different ways and have fun doing it in different ways. So therefore, I am all in favor of it. I see no downsides. Gregory Kusnik says, have your wine buying habits changed since leaving California? Yes, for the worse. Actually, that's not quite true. It's been more difficult. California, you can just get all the wine you want. It's very easy. We were huge fans of K&L wines. If you live in LA, or maybe I think they also have a San Francisco outpost. K&L is great. They have an elaborate website with many different wines, and they actually taste the wines and tell you about them, which is very helpful when you're buying them. And then they will deliver them to your house. Like, you just buy them online and deliver the wines. That's the way life should be. Maryland is much more uptight about that kind of thing. So fortunately, there is a Total Wine store not too far away. Nothing in Baltimore is very far away from anything else. That's very much unlike LA. You can actually travel anywhere in Baltimore very easily. So we often go to Total Wine, and they have a huge, wonderful selection, including of the kinds of wines that we really like. The owner of Total Wine is now running for Senate in Maryland. I don't think that I'll be voting for him. He seems like a decent enough fellow, but I kind of like his opponent in the primary a little bit more. But I haven't yet taken the time to look into that carefully. It's one of those things where their policy proposals seem to be more or less exactly the same. So it's a matter of, who do you trust, or so forth. So it's a little bit harder to judge. And there's some other online places that you can order wine. But I think there's one place I order wine from online, and they do deliver it. I think it's illegal that they deliver it. I think you're not allowed to just ship a case of wine to someone in Maryland, and therefore most places won't do it. But some places will just do it. And I've never actually gotten in trouble by it, so I do it. Anyway, just so people know, like, our wine buying habits, such as they are not that sophisticated. We go through a lot of wine. It's almost always in the $20, $30, maybe $40 bottle range. We're not drinking $300 bottles of wine on the regular, much as I would like to. That and first-class plane tickets would be my major living habits if I suddenly became super duper wealthy. Like my house and my job I love, and I wouldn't even change. Even the cars I'm driving, I'm perfectly happy with. I would buy nicer wine. I would get nicer plane tickets. I guess after talking to Derek Guy on the podcast, maybe I'd start wearing bespoke suits if I became very wealthy also. Okay. Timothy Paget asks a priority question. A well-known physicist in a recent interview said, quantum mechanics is a deterministic theory. Absolutely, physics is deterministic. Schrödinger's equation defines exactly the underlying physical quantity of the wave function with exact precision. The measurements may be probabilistic, but it is defined with 100% accuracy, I mean completely. So my question is he entirely correct to claim the universe is fundamentally deterministic? Is it not true to view the universe as somehow fundamentally probabilistic in some meaningful sense? Look, this is one of the questions that depends on your perspective on the foundations of quantum mechanics. In many worlds, there's a very clear answer to this question, but it comes in two parts. The first part is the wave function of the universe evolves perfectly deterministically. It just obeys the Schrödinger equation, which is reversible, deterministic, information conserving, etc. But our observational measurements are not predictable. So that's why I'm confused by this quote where your physicist says The Schrödinger equation defines underlying physical with exact precision. The measurements may be probabilistic, but it is defined with 100% accuracy. So yeah, but measurement outcomes matter. That's what we actually observe in the universe. So in many worlds, the wave function is defined precisely, but the experience of any one person is not deterministic. So therefore, from the perspective of an individual, the world is not deterministic in many worlds. In something like the pilot wave theories, the Bohmian mechanics theories, it is a very similar situation, actually. The underlying dynamics are perfectly deterministic, but because the hidden variables are hidden, the best predictions we can make about the universe are probabilistic. It's a little subtle in that case because from the God's eye view, you might say, well, then I could know what the hidden variables are, and then you could literally predict what the future measurement outcomes would be. That's not true in many worlds. But also, you don't have the God's eye view, and you never will, so therefore the actual in practice distinctions are very minimal. Is it true? Yeah, of course, but then the final thing is maybe neither one of these is right. Maybe there's other options in quantum mechanics where things are fundamentally indeterministic and so forth. So I think we don't know whether or not the ultimate laws of physics are deterministic or probabilistic because we don't know what the ultimate laws of physics are. We do know that the experiences of human beings looking at the universe are not deterministic. They are not predictable on the basis of the laws of physics as we understand them. There you go. Philip Grant says, if you had to recommend someone inside or outside physics whose views you consistently disagree with but are consistently worth listening to, who would you choose? I think there's lots of people. It depends what you mean by consistently disagree with. Like, obviously, I think it's okay to want people to have some underlying shared values for someone who you want to talk with all the time. You want to be engaged in a good faith seeking of the truth, even though your individual tentative conclusions about what the truth is might be very different than somebody else's. I don't have any interest in talking with people who disagree with me because they are bad faith grifters or con men, okay? That's not really my goal. But I have people on the podcast who I disagree with about important things. David Chalmers was on the podcast, completely disagree with him about consciousness, which is what we talked about. David and Dan Dennett had huge disagreements, and they were also great friends. And David was really broken up when Dan died, for example. Tim Maudlin and I disagree about everything about physics, but we have very useful conversations. I'm always happy to talk to Tim. He's a super smart guy. I had a good time talking to Neil Ferguson on the podcast about more political things, even though we disagree about those. There are religious people. I went to a Catholic university and talked to a whole bunch of religious people who I disagree with deeply about things. So, there's lots of people out there. I think it's more about sincerity, intelligence, open-mindedness. They might think something, but they want to think it for reasons that they're willing to change their minds about if they have good reasons to do so. That's what I look for in someone to talk to. Johnny says, what is the work you're most proud or happy about? It could be a book or paper, or even just teaching someone. That's always hard. I have different, there's nothing I've ever done that I'm perfectly happy with. Let's put it that way. There's very few things I've ever done that I'm perfectly unhappy with also. In terms of books, I think The Big Picture is my favorite book. That was the one that I sort of always wanted to write, and I think I did a pretty good job writing it for the most part. It's one of those books when I pick it up and I leaf through it for some reason, I'm like, yeah, okay, I did a pretty good job there. In terms of scientific papers, ironically, the paper I wrote with Jennifer Chen on the arrow of time and time-symmetric universe, number one, we never got it published. Not because we couldn't get it published. We easily could have gotten it published, but the timing was bad. I left the University of Chicago. She graduated and so forth, and we just never submitted the revised version to the journal. And we didn't care that much, so that never happened. And also, I disagree. I think that I would have improved. There's certain parts of the paper where the calculations could be done better than they were. The underlying spirit of the paper, though, I think is both an interesting new idea and could even be right about this large-scale structure of the universe, right? It's not often that you have an original idea about the structure of the universe that has a chance of being right. I don't know what that chance is, but it's still, to me, the most fair and compelling version of a cosmological theory that tries to account for the arrow of time. So I like it for that reason. There's other things I like for different reasons. I wrote a paper with Alan Guth and Eddie Farhi and Ken Olam on time machines, closed time-like curves in 2+1 dimensional gravity, where I did something that was very mathematically clever, right? And that always feels good, but no one cared about that paper. So it's not like a major contribution to science or anything, but I did something good. That always is nice to have a feeling about. Marco Tauser says, I sometimes have the impression that public intellectuals and science communicators overestimate the breadth of their reach. How much do you know about the demographics of your audience? What fraction have degrees in physics, PhDs, etc.? I'm not sure where you get the impression that public intellectuals and science communicators overestimate the breadth of their reach, because I have no idea what the breadth is estimated to be, much less what it is. I don't know. Like, literally right now as I'm talking, I'm alone in a room talking to a machine, talking to a microphone that is recording in the on the computer. I can't see what the results are, right? When I put the podcast out there, I get, I don't know, dozens of responses on, Patreon and on the website and on YouTube and whatever. I know that the typical numbers for the people who listen to an episode of the podcast are of order 100,000 people, about 50-50 in the US and elsewhere. I don't have any real information about their education level, their ages, their genders, or anything like that. For books, I have approximately, the number of books I've sold, and my best-selling book has sold more copies than a typical podcast episode, but my worst-selling books have sold less. So that's the rough order of magnitude there. It's not very big. 100,000 people is not very big in the history of the world. But of course, if 100,000 people listen to each episode, it's not the same 100,000 people. Likewise for the reading of the books, for the watching of the YouTube lectures. I think I don't know what my most watched YouTube lecture is, but it's well over 1 million views, right? So that's getting to be serious numbers when it's well over 1 million views. It was 1 million people who watched me on the Colbert Report, although it was only just telling jokes for 5 minutes, right? But the general relativity episode of The Biggest Ideas in the Universe is an hour and a half of me doing tensor calculus, and it has over 800,000 views last I checked, which was a while ago, which warms my heart. It really does. Still, I don't think that's in any way a huge reach compared to the number of people in the United States, much less the number of people in the world. So no, I don't think that the reach is very big in any objective sense compared to actual celebrities or well-known people, etc. So that's okay. I'm not. If 100,000 people listen to this Ask Me Anything episode of Mindscape, my response to that fact is not, oh my God, why don't I reach 10 million people? This is terrible. My response is, oh my God, I'm reaching 100,000 people. That is awesome. It's a lot more than I reach, when I teach a class or anything like that. So that's why I consistently say over and over again, I'm hugely grateful and warmly appreciative of everyone who listens to Mindscape. Last question of this AMA is from Joshua Rubin, who says, what is your favorite poem? So I'm actually going to give you a little bonus for sitting through this whole AMA, which is I'm going to read 2 poems to you. How about that? Because I don't have a favorite poem. I'm not a super poetry guy. Like, I'm not a big expert. But I like it. When I'm reading my relationship to poetry is exactly the same as the relationship that I have to classical music. I like it when I hear good stuff, but I'm by no means a connoisseur or an aficionado. So I'll read what used to be my favorite poem when I was younger. It's by William Butler Yeats. It's a famous one. They're both famous ones. These are not like plucked from obscurity or anything like that. So this is When You Are Old, which you may have heard of. And he says, pardon, these are medium-length poems, so you don't need to listen. You can turn it off. That's fine. When you are old and gray and full of sleep and nodding by the fire, take down this book and slowly read, and dream of the soft look your eyes had once and of their shadows deep. How many loved your moments of glad grace and loved your beauty with love false or true, But one man loved the pilgrim's soul in you and loved the sorrows of your changing face. And bending down beside the glowing bars, murmur a little sadly, how love fled and paced upon the mountains o'erhead and hid his face amid a crowd of stars. So that's, maybe a shortish, medium-ish poem, but very beautifully written. Yeats was a genius. This is, the tiny bit of pride I have in my quasi-Irish heritage. It goes back to their literary prowess. Yeats was pretty good at manipulating words. And it's beautiful, and it's a love poem in some sense. And I appreciated it for a long time because I'm not very good at reading poetry. Like, this is not my expertise. It took a long time for me to figure out how really deplorable was the sentiment being expressed here. Of course, Yeats is expressing love, in very beautiful, moving, powerful language. But basically, at the end, what is being revealed is he's talking about the love he had for someone else who didn't love him back, or at least who maybe loved him for a while and then stopped loving him. And then basically what he's saying is, you blew it. He's saying, you're going to regret not loving me back. That's not a very good sentiment to really place a whole poem on. Like, Yeats is still a little peeved that this person didn't love him back as much as he thought he deserved. It's a little selfish, I think. So I moved on from that poem and I went back in time. Here's another one which I read in college, but it had the opposite effect. I read it and I thought it was kind of fun, but didn't love it. And then the more I thought about it, the more I loved it. And this is a classic by John Donne, one of the metaphysical poets, called The Sun Rising. It's a little longer, so put up with me. Busy old fool, unruly sun, why dost thou thus through windows and through curtains call on us? Must to thy motions lovers' seasons run? Saucy pedantic wretch, go chide late schoolboys and sour prentices. Go tell court huntsmen that the king will ride, call country ants to harvest offices. Love, all alike, no season knows, nor clime, nor hours, days, month, which are the rags of time. Thy beams, so reverend and strong, why shouldst thou think? I could eclipse and cloud them with a wink, but that I would not lose her sight so long. If her eyes have not blinded thine, look, and tomorrow late tell me, whether both the Indias of spice and mine be where thou left'st them, or lie here with me. Ask for those kings whom thou saw'st yesterday, and thou shalt hear all here in one bed lay. She's all states, and all princes I, nothing else is. Princes do but play us. Compared to this, all honors mimic, all wealth alchemy. Thou, son, art half as happy as we, in that the world's contracted thus. Thine age asks ease, and since thy duties be to warm the world, that's done in warming us. Shine here to us, and thou art everywhere. This bed thy center is, these walls thy sphere. So if you get the spirit of it, he's talking to the sun, and he's saying that, he's in love, and he's sort of blissfully in love and honestly and truly in love, so much so that he's exaggerating the idea that when you're in love, all that really exists is you and the person you love. So he's saying basically, look, sun, I can turn you off just by blinking my eyes, by closing my eyelids and you disappear. You're not that big a deal. In fact, your only point is to keep me and my lover here warm right now. That's all that matters. And he does it in very, lovely language also. And so in my more mature phase of life as I am now, in someone in a good and happy relationship, this is what is a good love poem to me. The sort of teasing way in which you can sort of metaphorically express that all that matters is you and the person you're in love with. And we know that you can't maintain that 24/7. That's okay. But in the moment, that's how you're feeling. Can't think of a better way to end the AMA than that. Thanks for listening. Huge thanks to all the Patreon supporters who support Mindscape. See you next week.